Okay, so actually the real thing I wanted to ask you a bit about is some of this mathematics stuff, because I think I'm quite a bit stuck, and I think you probably have some ideas here.
Okay.
But let's just,
Euclid Book 2, Proposition 8.
I'm trying to do empirical mathematics.
Cool.
All right, let us ponder this question for a moment. All right, so your claim, well, let's make your average multi-way causal graph, okay? Let's take, this is becoming my go-to random whatever, okay. All right, let's go this. All right, there we have our states graph. Now let's make our causal graph. Okay. So let's okay, dandy. All right, now the question is what to do to think about what the kind of the analog of the Penrose diagram for this is. So we're squashing, I mean, in a sense, let's make it like a Penrose diagram. It's kind of a story of particles are like black holes type story.
Right.
You know, I mean, although maybe they're black holes in this case in Branchial space. Okay, so what will we actually do here to compress this guy? So what we want to do is to preserve some kind of global causal structure. Okay, so what we might say is the scattering process might correspond to the causal structure, Penrose-like causal structure of this graph.
Mm-hmm.
Oh boy, if this really works, this would be crazy. So this would be, so the idea would be that for a given causal structure of this graph, or overall causal structure, causal connection structure, there are many underlying specific Branchial graph, multi-way graphs that will do that.
Right, right.
And
yeah,
go ahead.
I was going to say, my point is only that the Penrose diagrams are just a diagrammatic representation of the causal partial order in space-time. And so the conjecture would be Feynman diagrams are a diagrammatic representation of the evolution causal partial order in the multi-way causal graph.
Okay, but that has the implication that essentially, what we're saying is there's a particular scattering event,
mm-hmm.
which in the space-time case will be a black hole scattering event, essentially, as represented by the Penrose diagram. Now, what one's saying is, if we then, there's an equivalence class of these diagrams that all correspond. That's not right. It's not right because there's just one of these. I'm trying to understand, how do you get
one of what?
the multi-way causal graph? Oh, no, but there isn't, because given a particular preparation of an initial state, there are many multi-way causal graphs consistent with that preparation of the initial state.
Right.
So then, consistent with a given scattering event, basically. Scattering process. So then the absolutely totally bonkers thing, if it was true, would be that the Feynman diagrams would correspond, we could get them from path weights from these things.
Yeah, that was my point, right? That you define an equivalence relation on time-like paths through the multi-way causal graph, and they give you paths in the Feynman diagram.
But I mean, the concept, okay, on the grounds that in a Feynman diagram, you are eliding space. No, so in a Feynman diagram, you are representing time-like connections, time-like, orderings, but space has been collapsed, basically.
Right.
So let's take this as an example. What would we actually do? So we would take.
So you'd take a collection of paths.
Yeah.
And then you would just collapse some of those paths together.
Yeah, but which paths? I mean, in other words, which paths are not equivalent? Which paths are considered an equivalent? And maybe this particular multi-way system doesn't have the necessary kind of.
But it depends what process you're trying to model, right?
Well, I know, but let's say we're trying to model a scattering process, because that's what Feynman diagrams are about.
But is there any scattering process happening here?
Probably not. Probably not. I mean, probably need a more complicated initial condition and so on. Right, but so in the story of, I mean, let's consider, in the story of our absurdly simplified business of, let's just do an XY whatever thing, right? Mm-hmm. What would the multi-way causal graph look like for these cases? So imagine that we just have one of these rules, the XOOX rule, right?
Yeah.
I think that we don't have particle creation in the quantum mechanics that you were looking at.
Why?
Well, because you need more X's to be generated.
We have field operators that say O goes to X.
All right, fine.
Right.
Well then, okay. So then, give me an actual concrete multi-way rule that we could use here.
For what?
Well, to try one of these. I want to try making a scattering process with two particles coming in, and let's say two particles come in, and then we'll look for. Then what we're interested in is, let's say, 2-to-2 scattering, where two particles come in, and then we're going to filter what we're looking at for final states, which correspond to, two particles going out.
Right. Yeah, I can construct one of those.
Is it easy to do? Can you?
Not live, but no, I've been looking at similar things in the course of doing this interference stuff. I was creating kind of idealized particle accelerators and things.
Okay. Well, anyway, I think it's worth looking at that. And then the question is to look at, for example, if we can get 2-to-2 scattering, which means that we're basically, I'm just wondering what then, So implicitly, there is a certain Lagrangian that this thing is operating with.
Mm-hmm.
And the question then is how, so that Lagrangian, the claim is that if we look at this multi-way causal graph and we look at sort of divergences of causal edges there, that we should be able to see what the effective Lagrangian is.
Mm-hmm.
Yeah.
I've just discovered if I run one of these for a very ideal, for a simple kind of two particle interaction, and then just do community graph plot on the causal graph, you get something that's not totally unreasonable.
What is that? Send me the code. What?
I mean, so if I don't know, this is probably a bad example. If you run something like this. So then you can do, if you find the graph communities, you will find the ones where.
Yes. You're saying this is, what the heck is this? So what is your claim about this? That these are,
because there are two x's here, right? That are jumping around and then they hit each other and they interfere.
yes.
Right. And so if you, I'm looking through the graph communities at the moment, and so it seems like they're bunched. The ones that are bunched together are, the left x pre-impact, the right x pre-impact, and then the left x and right x post-impact. So in the early stages, the causal graph won't join up. Right, there you go.
And let's see, we probably could get the causal graph removing earlier stages of the causal graph, right? How would we do that? We could just do that by...
You could, is there a graph difference? There is a graph difference, isn't there?
I think there's a graph difference, yeah.
Yeah. Graph difference n minus 1.
Right.
Oh, by the way, sorry, this potentially seems relevant, although I haven't read it. I've only read the abstract.
I recognize the name of that first person. I've interacted with that first person. What the heck are they doing, though? Let's see.
So they're making use of some formal analogy between two-level quantum systems and Dirac electrons to say we can model, qubit, we can model interactions between pairs of qubits as, using techniques of quantum electrodynamics.
Yeah. So this is quantum mechanics of zero-dimensional quantum field theory.
Something like that, right? My point is, this would be the direct analog of black hole scattering or something.
Yeah, that's interesting. So this is QM as zero-dimensional QFT. We should put this paper in our external reference collection.
Yep.
But let's just do this graph difference thing. Hold on one second. I was almost there.
There are tendrils. Whose significance I do not understand.
Well, I got a different answer here. Let's see what happens here. Graph structure.
Oh wait, you're differencing out all of the previous ones.
No, I'm not. I'm differencing them by pairs. I'm doing n minus n minus 1.
I see.
Oh, you know what I've got wrong? I need to do a reverse.
Okay. My more simple-minded technique of mapping over a range to comma whatever yielded a different result.
Well, I mean, you can obviously just compute the thing explicitly by doing a. I was just trying to avoid recomputing the thing. Hold on one second. Reverse of that. There we go. You got the same result?
Yep. Yep.
What the hell does this mean? Well, first of all, I don't understand what the graph communities mean here, really. What does a graph community mean in a causal graph?
Well, it means that there's a cluster of events that are not particularly causally related to another cluster of events.
Indeed. What will we expect this to look like? So the ones that are closely causally related might be events associated with one particle, and then the others are events associated with the other, like this could correspond, each of these clumps could correspond to a particle and its effect, the propagation of that one particle. And
right.
These could correspond to scattering.
Mm-hmm.
So how will we test that hypothesis? Okay, let's just think about that for a second. So this, well, one thing to do is to trace one of these clusters. Yeah, this is like each one of these, this is like some kind of sheet that represents the interactions going with time, because this is like, I don't know which piece goes with which piece, but that will be the thing to figure out next is which events knit together with which events.
Well, actually, hang on. We can make this a bit easier. If we change the rules so that one particle is treated with x's and the other particle is treated with y's, then at least we can test which event, which event is acting on which particle.
Right. So you've got so we'll have both the X rules and the Y rules here is what you're proposing.
Right.
But then
right,
what's
exactly.
the XY joint rule, or isn't there one?
There shouldn't be one, right? The absence of the XY joint rule is kind of the analog of the scattering process, right? Because you're saying once you have X and Y and they're contiguous, then your system is no longer as free as it was.
Right. Okay, so here, so we go 6 steps. Okay, so now we should be able to color these things based on whether they are, I don't know whether they, what are the event structures here? What are
So all you really care about is if you look at first of event, or actually you could even just say first of event, does it contain an X or does it contain a Y?
Okay, that's
the rule that's being applied. CG select vertex list.
I wonder how we determine in the community graph plot, I wonder how we determine the colors there.
Hey, cool.
What happened? You sent me the code?
Yeah, sure. So it's nothing particularly sophisticated. Let me just put it all together. It's kind of exactly what you would have expected. There you go.
I want to see it anyway. All right, so let's take a look. Okay, so what's this showing us?
So yellow is one particle, red is the other particle. So it's showing that the two obvious communities there are indeed divided along particle lines.
As opposed to party lines.
Right.
As opposed to that social laser.
I still need to read that paper. That looked like a lot of fun.
I think it was kind of amusing, yeah. Okay, so let's understand this. So if we are doing now, can we do our okay, fine. So you've got this. So what we want to do probably.
We could also do a more fine. Hang on, sorry, I'm gonna.
Yeah, okay, but we can also do this on successive steps. What are these clumps? What are the clumps inside the clumps here?
Clumps inside the clump. Oh, I don't know.
They have a distinct interference fringe type story. I mean,
this is the same rule that would give you interference fringes. So yeah, it's probably that.
But the question is whether, but that's interesting in its own right. If in fact the interference fringes can be seen in branchial space.
Yes, I agree. That is cool.
But which we should be able to see. I mean, in terms of, let's see, and if we do, let's just do the diffraction rule. What is it? Do you have your diffraction rule readily at hand? What is the I can just do the same thing with, instead of just one particle and and just a single lump in the middle here.
Yeah, just have X surrounded by preferably a symmetric number of O's.
That was very boring.
I guess as you as you would expect.
What? Well, let's see. If I have multiple X's here.
Oh, then it's going to get interesting, yeah. Because now that's more like a double slit.
If this starts forming diffraction patterns, this is just absolutely, totally bonkers.
I think I'm pretty sure it will, right? Hang on. I mean, I can probably construct a minimal example that will. If you want to see the double slit interference fringes, I think that's quite easy.
In Branchial space.
Yeah.
I mean, it should happen. I agree. It absolutely should happen.
Yeah, they even get laid out quite nicely.
I know. Look
Yeah,
at this. Look at this. Look at this. But I can see them here. Well,
yeah.
here, let's do. That's just crazy. That's just crazy.
It's great.
Let's just try to understand exactly what we're seeing here. So what we're seeing, if we were to take the difference causal graph, we will see the propagation of these things through time, right?
Uh-huh.
So let's compute this thing. Let's just do it in the Neanderthal way. T minus 1. And the category of this doesn't take much computation time. Let's avoid making a mistake. Okay, so let's say we want to look at this. T goes up to 6. What happened here? Oh, because the graph differences were no longer beautifully colored.
You know, we could do something.
It's a little less clear what's going on here. What's that?
Sorry, no, I'm doing something that's kind of hacky, but might be informative. Give me a moment.
Okay.
Okay, these are quite fun. Here's a toy Feynman scattering process kind of thing.
I want to understand what I also got with that layered causal graph.
So the red and yellow highlighted vertices correspond to the left and right particles. So they hit each other and they scatter.
What is going on?
It's perhaps easiest to see if you look at the transition between the 6th and the 7th. So you see in the 6th one there that there's two independent things, but by the 7th one they've joined.
Wait, what are you saying? 6th one where?
The 6th multi-way causal graph, the one just before they join.
Yes.
Right. So if you have a look at that, you'll see that there are these two lumps. One is red, one is yellow.
Yes, I see
the
that.
two particles. And then so then if you look at the 7th, you see the point where they first make contact.
Yes, I understand that. And then they make a bound state of some weird kind.
Right.
How am I supposed to understand this thing? Is it a bound state or what?
No, so this is one particle scattering off the other, right? Because what the rules are saying is the X particle moves to the right, the Y particle moves to the left. Then when they hit each other, they swap around. So then one of the particles now starts moving to the left, the other one starts moving to the right.
Yeah, I understand. But so I see. So what we need again is the graph differences here.
Right. You can run your magical code.
Well, I can run that code, but I want to show you this piece, this thing here, which I don't understand. Okay, so that's the layered graph corresponding to this.
Yep.
Right? So this is a projection downwards of the sky. So this is the time evolution that should be building up these interference fringes.
Yeah, I understand. It's a multi-way causal graph.
Yeah, right. But I am having a hard time seeing. See, we're seeing density here of causal edges, of points rather, and I'm trying to understand where I see that in this picture. So we can see the sort of space-time development of this interference pattern, if it's an interference pattern.
But the point is that the interference fringes are a cumulative effect.
I know that. I know that. But
so it makes sense to project. It doesn't make sense to view it as a space-time. It makes sense to project it down.
Well, I realize that. I understand that. But it will be nice to see their development over time. And what, this is in a sense the space-time. Okay, what on earth is that? Well, those are probably, they just didn't interact.
Yeah, if you go to 5, they should.
Okay. What is that? I mean, clearly laying it out in one dimension isn't very convincing. Oh, you know what we need to do? We need to do the 3D layered plot. What is that called? That is called graph 3D. Because this at least has a chance to give us. Oh gosh, what is it doing? Come on. Absolutely frigging useless. What the hell? It's a frigging pancake. Not useful. Distinctly not useful. Well, that's not very helpful. These graph differences fall apart.
Yeah.
I'm still exercised about this. I mean, this is very cool. If this is let's just understand what this actually is. So this is claiming that there are particular well, what are you in the process of figuring out?
I'm trying to define an appropriate equivalence relation on these paths so we can better see what's going on. But I don't yet know the best way to do that.
Which paths?
The paths in this pseudo Feynman diagram thing. Because there's a huge amount of redundancy, and I want to figure out how do we trim away all of that so we can just see two paths. One being the yellow one, one being the red one.
Right. Well, I still want to, can we just come back to the interpretation of what's going on here? I mean, for example, in this picture here, our prize interference picture.
Yep. Oh, by the way, I figured out that the highlighting was wrong because it was reflecting. Sorry, it's a really obvious bug. When the things hit and they reflect, suddenly it starts highlighting the other one because it's now switched to an X. So to impose continuity, I've changed it to this, which makes it less obscure, but only slightly.
Wait a minute. So should I correct this? Are you saying this is an incorrect piece of code?
Yeah, right. Well, I can send you the correct. Hang on, wait. Give me one moment. I can send you the correct thing. It's only a small change. Yeah, hang on. Oops. For some reason, Zoom chat is being strange. Oh, there you go.
So that's a corrected version of that code there.
Should be, yeah. So all I'm doing is I'm just, when they get reflected, I'm changing them to A's and B's so we can continue to plot sort of continuity.
Okay, so I don't understand this at all. You're saying, I'm sorry, I'm still exercised about what's going on here.
Okay, why?
So, well, the claim is the graph rendering in the diffraction pictures that you were making before, your coordinates are determined by actual, where is the x? They're sorted by where is the x, okay?
Right.
Now, in this case here, what's happening is these are regions that have higher connectivity.
Right, because the rules are local.
Yeah, I understand. So the rules are local in position space.
Yeah, so there'll be more causal connections between local points in the multi-way causal graph.
Between spatially local points.
Right.
Okay. Okay, so that's saying, what is this saying? So this is saying that there are spatially local points in which there is more there would be a spatial point that would correspond to something here, but this is saying that there aren't. I'm a little confused. Can you how would you explain what you see here?
Well, over time, one sees interference fringes that are localized in space. The rules are localized in space, and hence the causal connections between events are localized in space. And so the bunching of, particle events on the back wall in space is reflected as a bunching of causal relations in space in the multi-way causal graph.
Yeah.
Isn't that what you expect?
Yeah, it is more or less. But why do we not see anything build up in space-time?
Because it's a cumulative effect. Each event is instantaneous.
Yeah, right. I understand.
Each time a particle hits the back wall, it's an instantaneous event. There's no propagation forward. So you only see the cumulative buildup if you project downwards on the time axis, which you've explicitly not done here.
It still surprises me. This may be a bad graph rendering that we've got here. It still surprises me that we're not seeing. So this bunching and, look, if we were to lay these out in space, right? If we were to lay out.
Why does that surprise you? If you imagine a space-time picture for a beam of particles going through a pair of slits, why would you expect there to be bunching in space-time for what is a cumulative spatial effect? Maybe my intuition is wrong.
You wouldn't have it, but I don't get it. I don't get it. Here, look, we can clearly, if we know each one of these events, right, we can attribute some spatial position to that event by looking at what the X's and O's were for that event, right?
Yep.
which this may or may not have successfully done. And, we know the time ordering of these events. It really surprises me that we're not seeing this thing, because it's like we move back the back wall. This number here determines sort of how far back the back wall is.
Yeah.
Right? It bothers me that we're not seeing this in build up. I bet we would if we laid this out better. I bet what we would see is, yeah, I don't understand why you think we wouldn't see that. I mean, in the physical case, I would expect,
you would expect to see bunching in space, not in space-time.
Absolutely. But since this, as we move back the back wall, for every position of the back wall, we will see bunching. Therefore, one would expect to see in here, I would have expected to see stripes in here forming.
Which we do.
Well, I don't see that here. I mean, we sort of do.
Well, no, in the multi-way causal graph projected into the spatial direction.
I know that. So we could solve this. Look, if we take this thing here, okay, we've got the multi-way graph, causal graph, and we say here it is. Let's just take the 5-step one of these, okay, and now we say, okay, so how would we make coordinates out of this?
What do you mean?
Well, I'm trying to get our approximate, where would we attribute the spatial location of that event to be? Which is what you're doing to actually make diffraction patterns and so on.
Right.
Okay, so given these two events, this is the initial state and final state, yes?
I'm sorry, what's initial state and final state? These are just events.
No, I know that, but in each event, what you're saying is this initial state maps to this final state. Is that right? No, it's not.
No, that's the prefix and suffix. It's rule, input, prefix, suffix.
I see, okay. So if we were to try and attribute which sort of a spatial position to this event, we could do that by looking at the relative size of the prefix and suffix, couldn't we?
Yeah. Right. Well, I mean, that would be string. If you want your coordinate system to be the string position.
Exactly. So what I'm saying is,
right, rather than the spatial position.
Right. Fine. Yes. Now, how do we get a? Let's see. How do we get a time coordinate here, which is that's based on what's that? Okay, fine. Great. Let's do step number. Okay, how do we do that with this?
Include step number.
Okay, so then what we would do here is, for each vertex, we would take, we want to get a y coordinate. So we would say, this thing here, t blank arrow, blank arrow blank. We don't care about that. We probably don't care about that either. And we say s blank blank, and we would say, let's see, string length of s minus t. Okay, so then what we would do is we would say, for this thing here, what we want to say is vertex coordinates That's odd. My God. Oh, silly me. Aha. Look at that. So there are many. Oh, I see. What we really need to do is not, this is putting many events on top of each other, right?
Mm-hmm.
So what we really want to do is, instead of the coordinates just being string length, we want to have them, but that's the basic structure of what's going on.
Right.
And that's saying that these are the regions that presumably, these are the places. I'm a little confused by this. I mean, in other words, how do we get, oh gosh, I'm not understanding this. So how do we get a finer grained sense of coordinate position from these than just using string length of where the event happened, so to speak?
And again, are you talking about string coordinates or spatial coordinates?
Well, I want to map it to spatial coordinates.
Okay, well then we can just use my spatial coordinate scheme, the one I
Okay.
used in the diffraction bulletin.
Okay, which works like what? What do we have?
You take the sum of the string positions of the x's, and then that tells you which region the photon is contained within, and then you take the difference, and that tells you within that region where the photon is.
Do you have a piece of code that just does it?
Well, there's the function string position.
Okay, but so what you're saying, string position of, we've got an x here. So you're saying we reconstitute the string, right?
Yep.
We have to reconstitute this whole string.
Mm-hmm.
So that's saying,
so it'd be string join hash of 3, 1, hash of 1, 2, hash of 3, 2.
This thing here, this one here is the thing in the middle, right? Is that right? Is that the left-hand side? Yes, that's the left-hand side.
That's the input for the rule.
Okay. Okay, so here then, we've got those three pieces, and then you're saying it's string join of S1, Si, S3. Right?
That will give you the input rather than the output.
Okay, what would you like? You like the output. Is that right? You're saying we want the output, so that this is then the Si blank is there, correct?
Sure.
Okay, so that's the output. Okay, so now what do we do with this? So now we're saying in that there's a string position of X. Okay, how many X's will there be? There's just one X in all of these, right?
No, there'll be two.
Okay,
it's
so then what?
It's a two-slit diffraction.
Okay, so then how do we compute what we want the position to be? Given that we've got that string position, so that will give two values there.
Right. So then if you map first over those values, that will give you the actual positions rather than just the beginnings and ends. And then if you take the sum, that will tell you whether they exist in the central separator region, the right slit region, or the right separator region.
Okay, all right.
And then
So
if you take that difference, it will...
Let's take an example here. So let's take this thing here. Okay, 7 minus 5. Oh, it's minus 5 is irrelevant. Now, why? There's only one X according to this.
What?
According to this thing, it's only
two X's.
I know. So something went wrong, right? So the string join of S1, which is there, the prefix.
No. You're calling get coords the old function get coords.
That will be better. Okay, so each of those I want to map first onto that. Okay, fine. So that's the positions of the two x's. Now, what are you telling me to do to the positions of those two x's?
So take the sum to tell you which of the, whether they exist in the central region, the slit region, or the right separator region, and take the difference to tell you within the region where the photon lies.
Okay, but so we're trying to get a single coordinate. So what's the value of that single coordinate?
It depends on the size of the separator regions.
That's what I thought. Okay.
But basically, it's sum multiplied by separator region size plus difference.
Okay, so let's say this is going to be a separator. So this is now LR separator. All right, you're telling me it's sum multiplied by separator region size plus what?
Plus difference.
L minus R or R minus L?
Absolute value of whichever.
Okay. Let's see, how big is the separator region here? Is that 3? Does that count as 3 there?
Yeah, I think 3 is the minimum for which it'll make sense.
Okay.
I have no idea what this is going to yield.
Well, that's why we're doing the experiment. Okay, well, it's nice and regular, which doesn't surprise me, but what is it showing us? So this is showing what the heck is this showing here?
It's not a graph plot.
Doesn't matter. Should be able to get. Oh, it's got
coordinates.
Well, I wonder what happens if I say show.
Also,
weird.
You could just multiply the minus t by something, right?
Yes. Okay, what the heck is this showing? All right, let's indeed multiply the minus t by, what would it be? I don't know what it's equal to. But okay, so what is this showing? This is showing going to particular spatial coordinates. It's not showing path weights in the multi-way graph. It's showing something different. What is it showing?
It's showing causal path weights.
Yeah, what does those mean? They're fairly uniform, it looks like, in here. So I don't understand where the bunching is going from.
It's coming from the fact that when you project down in space, they bunch.
But we
It's
are
a cumulative
projecting.
effect.
I know, but we are projecting in space here. So you're saying
No, we're not. We're laying it out in space-time.
I understand that, but to project in space, all we're doing is crushing it in the vertical direction.
Yeah.
Okay, so what you're claiming is that if we look at, you're claiming that basically, well, actually,
All I'm claiming is it's a cumulative effect.
no, I understand, but what you're saying is, if we were to look at, we've got all these points in, we've got a limited number of spatial positions here, right? And you're saying that some of those spatial positions in this situation, they are, what we saw was that they're more clustered in this sort of causal space in some places than in others. And I'm not really seeing that here. And I would expect to see that as a, I mean.
Right, you would see it if you project down in space.
Okay, well, so let's, I mean, one way to do that.
Right, I mean, that's the reason you were seeing it before, isn't it? Because you're not making it, because those graphs don't make a distinction between time and space.
I understand that. So if we did this, for example, that's not very helpful. I just don't understand how you get from something which shows no such bunching. Okay, I don't understand the physics of what's going on. I'm confused because.
But I don't understand what's confusing. I mean, so there's, okay, you look at a space-time diagram of a beam of photons going through two slits.
Yep.
Each impact of a photon on the back wall is an instantaneous event. So in space-time, there is a completely, in space-time, the whole thing looks completely uniform. If you only track individual instantaneous events, there's no bunching. The only bunching occurs when you project down into, in space, and you see a cumulative effect of the photons, bunching in time.
Yeah,
if you show the thing in time, you're obviously not going to see that. So
I understand, but that's an essential feature of quantum mechanics, which is that, and I'm just surprised that we can't just see a little bit more constructively how it builds up from this picture. In other words,
you're surprised that this picture is consistent with what quantum mechanics says it should look like.
No, I mean, well, what you're saying is this picture is like doing measurements everywhere and you don't see an effect.
Right, you only see an effect if you have memory of previous measurements you made, because you can say, oh yeah, there's a photon that appeared here and I just saw a photon appear here, 2 seconds ago.
Okay, but that's wonderful.
Time, you don't see
that's wonderful. And I don't completely, it's wonderful, but I'm still, okay. So the point here is, in this picture, right, you're saying that if I were to look at the spatial coordinates here, that they would again, what would it do if I looked just at the spatial coordinates? So here I've got spatial coordinates and temporal coordinates, right? Let's say I throw away the temporal coordinates, right? So that everything is in spatial coordinates.
Yeah.
Right?
Then you would see bunching.
Okay, well, that's okay. So we can trivially do that here, right? All we have to do is change, okay. So then what we will do here is, so the bunching would be to say, I would like to take these events. I just like to make those events be identical, right? So I'm going to combine all those events. That would be what I would get if I were ignoring the temporal component.
Yep.
Right? So, but I also should be able to get bunching, if I'm not mistaken, if I just look at one time slice here. If I were to just take this thing how do I do that? If I say include step number, can I get like if I just look at the last two steps, is that a meaningful thing to do?
Yeah.
Okay. Do you think I will get bunching if I look just at the last two steps?
Last two, maybe. Yeah.
Yeah, I think it will as well. I just haven't well, I think we're really close to actually understanding this, but I don't understand it properly yet. In other words, you're saying that in sort of causal space,
All I'm saying is you can't see cumulative effects if you lay them out in space-time. That's what it means for it to be a cumulative effect.
no, I realize that. I realize that. I'm just, but
So
a cumulative effect is, you know, first you see this, then you see this, then you see this, etc. Right?
So you have to superimpose several hypersurfaces onto each other before you see the pattern.
I understand, but I'm expecting that, you know, like some Fourier series or something, you would see the pattern build up. Right? And that's what it's like, what would the pattern look like before it had gotten to where it's going, so to speak?
If you mean build up, you know, as you superimpose progressively more hypersurfaces, I completely agree. If you mean build up as in magically build up by laying out the effect in space-time, I don't understand.
No, but that's the point. Well, the point is that as you go down, right, successive levels here, you're saying the question is, how many levels do you need to see what amount of effect, right? You're claiming that a single time surface is not going to see the effect, right?
Yeah.
But you say, after I have a few time surfaces, I will see the effect.
Yep.
Okay. And the effect, so to understand that effect in time, which is not where interference patterns are usually thought about, to understand that effect in time, it's a correlation effect in time.
Yeah.
Which is just not the usual picture. Now, maybe in Bohmian mechanics or something, there is a version of it that looks like that. Is there?
What? Why is that not the usual picture?
Why is which not the usual picture?
Why is a correlation in time not the usual picture?
Well, let's think. If we solve the Schrödinger,
yeah,
then we will get, as a function of position and time, we get a certain amplitude.
Mm-hmm.
Okay. But what we're saying is, by looking at this back wall as a certain position, well, I'm sorry. What are you saying about the? Okay, we're going to solve the Schrödinger equation in space and time. We've got space and time laid out here. What is the relationship between anything we see here and psi of t, psi of x and t?
Well, I mean, if we coarse grain this by the evolution branches and we look at the state path weights, then we get exactly psi of t on each hypersurface, right?
But remember, this is a causal graph.
Yeah, so we have to coarse grain by the evolution branches, and then we get exactly psi of t.
By saying, because that's by coarse graining, you mean taking the path weights of all evolution branches.
No, I mean coarse graining and then taking the path weights.
What coarse graining in what sense?
In the standard sense by which you obtain a multi-way evolution graph from a multi-way causal graph. You coarse grain by the evolution paths.
I still think there's something interesting to find here. I'm sorry, I'm not as convinced that this is just, that I think if one understands this, it's going to show something sort of the insides of quantum mechanics of a kind that you don't see in the usual case, right? It's going to show you a sort of more microscopic level of what's going on than what you normally see.
I agree. That's why I wrote the diffraction bulletin.
Okay, but do you claim that you understand? But I'm trying to understand the space-time version of that picture. And you claim there isn't an interesting thing to figure out there. Well, anyway, all right, okay. I still think there's something more to figure out there. Maybe you've already figured it out, but I haven't. Well, and this is a potential scattering process here.
Okay. My point is only that, the measurement process is time extended in our models just as it is in ordinary quantum mechanics.
I get that. But you see, the thing is, okay, coming back to this, I understand that point, right? But so, for example, okay, your basic point is that, okay, first of all, the bunching in this causal graph reflects the fact that there are, okay, your basic claim is, what do you think will be seen if you look only at one slice here? Okay?
Yeah.
It's not obvious to me what you will even see. I mean, what you're going to see is
you would start to see a diffraction pattern, but only as a consequence of continuity of causal edges.
What? I mean,
any causal edges that existed on the previous hypersurface must exist on the present one, plus additional ones in the case of a growing rule like this one, right?
Yeah.
So
okay.
You are naturally coarse graining. So by projecting onto a hypersurface, you are naturally projecting everything above it as well. So of course you'll see a diffraction pattern. My point is, because it's a cumulative effect, you won't see that if you lay it out in space-time.
What do you mean you won't see it? You just said you would see it. You just said that on a particular slice
if you project down, if you project down in space, which you would implicitly be doing if you were to construct that, because of continuity of pathways.
But what is it that we're seeing here? We don't even have a graph here. At this level, all we have is a bunch of incoming edges from another level, right? Because these edges just go from one level to the next, right? So what we're seeing is in this graph here.
But the path weights tell you the number of evolution paths that led to that particular point. So it is dependent on the large scale structure of the graph. And the path weights are the things from which you compute the spatial intensities of the diffraction pattern.
Okay.
So yes, of course, if we project onto a single hypersurface, you get a diffraction pattern.
Okay, but here we don't have any path weights. So with this bunching here, there are no path weights.
Right, that's just a consequence of the fact that the rules are local. And so there's a correlation between the spatial coordinates and the degree of causal relation.
Okay, but is that the same as the diffraction pattern or not?
Yeah.
Okay, but one requires path weights and the other does not. How come?
Well, because in this, all evolution paths are shown. It's the whole multi-way causal graph.
fair point. So your point is, let me try to understand that. You're saying in this graph, this merge here adds two path weights, right?
Mm-hmm.
But you're saying that if I were to look at the causal graph here, what would happen? So here, AAB, wherever it is, what did it get to? ABB. I'm confused. Why do I not see it here? Where is AAB? It's there. I'm confused here. So you're saying that each path. I'm confused. You're saying that somehow what here we are, and kind of you're typing something, so I don't know that it's some.
Oh, sorry. Never mind. Sorry, I'm listening.
Well, I mean, I'm asking the question: is it obvious that okay? So the causal edge associated with this event. I'm confused. What is it called? Event states graph. What is it? The thing called?
What is what thing called?
The thing that has both states and events. States.
Evolution events graph. If you don't want causal edges.
Okay, and now if I do want causal edges,
evolution causal graph.
Okay, so your point is that in this picture, what would be two path weights wind up being explicitly represented by causal edges. Is that true?
Right.
And let me just see that. Where can I see that in this picture? Let's see. In this, is that totally obvious by the way this is constructed?
Well, it's true by continuity of causal edges, yeah.
Explain. I mean, in other words, given that you had a branch and a merge in here, right? Like the AAB merge here, right? That will get additional path weight to that. You know, coming out of that node will be additional path weights, which came from the two paths coming in here, right?
Yeah, that's what path weights are.
I know.
Mm-hmm.
So how do we see the analogous thing for the causal edges? In other words, you're saying the causal edges are each causal edge. I mean, there's no need to have path weights for causal edges because they are already accounting for every single event.
Right. If you have an event that's a consequence of a merge, it's naturally causally dependent on the events that were on the two branches that merged.
Yes, I get that. But so oh gosh, is
so
it obvious?
So the continuity of the continuity of path weights becomes continuity of causal edges.
What do you mean by continuity of causal edges?
That the outgoing, the sum of outgoing causal edges is at least as much as as the sum of incoming ones.
Well, wait a minute. Why is that? What? Explain that. I'm sorry, explain that. You're saying the sum of the outgoing causal edges to an event. There's a certain set of
to a hypersurface. It's exactly the same as continuity of state path weights in across branchial hypersurfaces.
Yes, the total state path weight going into a slice is equal to the total state path weight coming out. And the same is true for events, yes. But so what
Right.
consequence does that have? I don't get it. I'm sorry, I just don't understand what okay, here you're saying I just don't get this. I'm sorry. I just don't get I don't see how, I mean, it may be quite obvious, but it's not obvious to me. This is showing events laid out in space-time, right? And it's showing the number of causal edges that reach each event, right? And what I'm assuming is that if we were to count the number of causal edges reaching a given event here, we would see this kind of diffraction pattern like thing down here, right?
Yes. Yeah. If it's being projected correctly, yes.
But what does projected correctly mean? I mean, in other words, I can count the number of causal edges that reach that point there, right? I can count the number that reach this other point here, right? If I simply count the number of causal edges reaching each point, is that equal to is that equal to the diffraction pattern weight?
On a single hypersurface? No.
Okay, and then I'm going to ask about the difference between amplitude and intensity.
Okay.
In other words, is this...
Well, one is the square of the other.
I'm aware of that.
Okay.
But how do we get... what we are computing is the magnitude of the amplitude. Right? Not the square. Which is okay, but I'm just trying to understand how. Look, anyway, this is. I don't think you're in the right. I mean, you're not in the right frame of mind to deal with my slowness here. But
okay.
You're just. I'm not as confused as you think I am. I'm just. I mean, I may be even more confused than you think I am. But there's something here.
I don't think you're confused. I'm wondering what it is you would possibly expect to see.
I don't know.
And why?
I'm trying to understand Look, I'm trying to understand from as simple-minded a point of view as possible what I'm seeing here and why. This is a lovely effect that we're seeing these things bunching up here. Okay. But I'm not quite understanding if I take this picture, right, and I take each of these events and I say, where is it spatially, right? I should see something that is not that different from this, right?
Yeah, absolutely.
Okay, but so
as long as it's not extended in time.
Yeah, I understand, but all you're saying, you're making the claim that if I were to take this picture and all I'm going to do is to make an equivalence class of these things here, right?
Yeah.
That what I would see is a graph where what is true about that graph? What's true about that graph? So I've conflated, I've made an equivalence class of all of these vertical things here, right? So I can do that. How can I actually do that here? What I can actually do is I can simply substitute how can I do this? What's the best way to do this? I just want to say, I want to ignore well, it's basically ignoring the step number, right?
Right.
Right. So it is this exact graph, ignoring the step number, but laying it out by, I mean, it's the exact same thing we got before, right? It's this, and it's without the coordinates, ignore the step number, and remove the recomputation of the coordinates. Okay, and then magically we will get
because it's not time extended.
exactly what we had before. Right. Now, I'm trying to figure out how to make this picture see, look, if I take the things in here, for example, in that lump there, do you think those correspond to, do you think that lump corresponds to this collection here?
Well, I don't necessarily think it corresponds to that particular collection of 4 vertices, no, or 5 vertices.
Yeah, but you understand what I'm saying? That it corresponds to a spatially localized. If I were to label this,
because the events are local.
Okay, all right. So let's do the following. Okay, look, here's how we're going to do this. This should work. Okay, so this now, I claim, is vertex labels, arrow, okay, so the claim is, you see these vertex labels here? So the claim would be, what?
Yeah, the communities are correlated in space, because which will be the case because the events are local.
Okay, so therefore these numbers, which give the positions in space, right? That those numbers will tend to be clustered. Oh God. Well, let's see if I make those numbers, how can I do this? I can say, let's do this. Vertex size arrow. And then let's do is it vertex style? Is that how it works? Why are these values all so similar? Did I do something stupid here? Or is this L plus R times sep abs of whatever? Those values are all extremely similar. See what I'm saying? I mean, in other words, they're look, those are the values that I get out for the positions.
Yeah.
Do you have any comments on those values? So they go from.
Those look right. Yeah.
Why are they right? What's the min max? 26 to 66. Okay. How do I map these? If it's 26 to 66, I want to say, oh gosh, what is it called? The thing that maps that to 0, 1.
I mean, we can just
rescale.
Okay.
Okay, I do not understand this picture. So I took the spatial coordinates, right?
Mm-hmm.
And I am now in this bunching, right? I mean, maybe the spatial coordinates are incorrectly computed at the earlier stages. Do you see what I'm saying?
Yeah, right.
I think that's probably what's going on.
Yeah, I should probably do something that I didn't look at multi-way causal graphs for these diffraction tests yet.
I know,
that's
yeah,
probably
it's okay.
an obvious next step.
Look, this is probably, it's probably incorrectly computed, but this is not what you would expect to see here, I think.
Right. Yeah, but I don't know if that's a problem with the coordinatization or with my ability to visualize graphs. I generally think, as a general point of philosophy, I don't trust pictures as much as you seem to.
It's the only thing we have. Yeah, something is off here. Something is
right.
off. I mean, I think that. All right. Anyway, okay. Look, I really had wanted to ask you about something else if I could.
Okay.
Although this Feynman diagram thing is just extremely tantalizing. All right, listen, the thing I wanted to ask you about, this is a complete segue. We're going to talk about metamathematics for a second, okay? This is a complete segue, completely different topic.
I understand.
Okay. So, all right. Here's the point of view. In metamathematics, we have, we're building up this multi-way graph-like thing. There are details about exactly what kind of an object it is, which I think depend on what kind of logic you're using, whether you're using modus ponens, whether you're using equational, what you're doing, and I'm a little bit confused about that. Okay. I'm a little bit confused about, okay, so you're building this thing up. All right. Here's an analogy. So, roll the clock back to the ancient Greeks. They had two types of axiomatization. One was of mathematics and the other was of physics. At the time, the mathematics one worked out well. The physics one did not work out. As in, you start from a bunch of icosahedra or something and you don't manage to build up physics. Okay. But in a sense, what they started doing, and that's what this piece of empirical metamathematics, wherever it was trying to do, is that's Euclid, for example. That's the empirical metamathematics of Euclid. Okay, of what theorems depend on what. But in some sense, and this isn't quite the analogous thing, but in some sense, the progress of mathematics is an exploration of this potentially infinite multi-way graph-like thing that corresponds to the network of all theorems of mathematics, right? This is obvious, yes?
Right.
Okay. So similarly in physics, so many aspects of that network we expect to be full of computational irreducibility, right?
Yep.
Yeah. Okay. Similarly, many aspects of the corresponding thing in physics we expect to be full of computational irreducibility. Okay. The surprising observation is that in physics, 20th century physics has delivered, these large-scale facts about what is otherwise underneath, presumably, an irreducible computational process.
Yep.
Okay. So what I'm trying to understand is, in the metamathematical case, what are the analogous kinds of statements that one can make to the statements that the global 20th century physics statements that we can make about physics?
Mm-hmm. No, I understand. It's the same. It's the same problem we were discussing a few days ago.
Indeed.
Mm-hmm.
Yes, it's the same problem I've been discussing for weeks. Right. Okay. So what I'm trying to understand is, for example, there are certain mysteries of mathematics, right? What are some examples of mysteries? An example of mystery is, how come we're able to do mathematics? How come it isn't, just full of undecidability?
Yep.
And the mystery is, there's a question of, does mathematics become progressively more difficult? Or are we able, we seem to be at progressively higher levels of abstraction, but there isn't evidence that it's becoming progressively more difficult.
Right.
Is it? So, okay, so that's the setting. Now,
and I should preface this by saying my views are basically the same as they were when we last discussed this. So
which are what?
Well, so those examples that you give of mathematics, okay, so the first one being, these statements about 20th century physics are not statements about physics. They are statements about metaphysics, in the sense that they are, statements about general relativity are not specific. They're not peculiar to a particular rule set. They are generic features of any rule set that produce, causal networks that have limiting manifold structure and so on. Same with quantum mechanics and completable multi-way systems.
Exactly. Yes.
So the analogous universal statements in mathematics would not be mathematical ones, but metamathematical ones. And I think actually the examples you gave are good examples of those. The fact that mathematics is doable is the statement of the geodesic equation in metamathematics, and the statement of the progressive abstraction doesn't lead to progressive geodesic divergence is a statement of expansion of the universe in metamathematics. both of which are meta-math statements rather than mathematical ones.
Well, okay. Okay. I'm just trying to understand these. Okay.
Okay.
Yeah, I agree that these are meta-mathematical statements. That's the point. Yes.
Yeah.
Right.
Right.
But and I don't think it's correct to say that, I mean, yes, the whole point is, the surprise is that there are statements that can be made across many irreducible underlying rules of physics.
Yeah, and the same is true, and the same is true of those statements about mathematics. That those, those mathematics will presumably also obey geodesic equations, so we can make the same statements there.
Right. Okay. So what? Okay. So which geodesic equation? What geodesic equation are you talking about? You're talking about what are you talking about there?
The analog of the relativistic geodesic equation, but for mathematics. The
one with Christoffel symbols and things.
Yeah. Well, if you write it in a coordinatized version, in the metric.
So I mean, the other version of it is the statement that bundles of geodesics don't change their area. I mean, is that what you're? I mean, change of area of geodesic bundles and things. Is that what you're?
That's a statement of continuity of the Ricci tensor, right? From which the geodesic equation can be derived by an action principle.
What do you mean by the geodesic equation? What do you think you mean in mathematics by that?
Well, the fact that mathematics is doable.
No,
but a combination of the geodesic equation and the Schwarzschild solution, right?
I don't understand that. What I mean, the fact that, but what do we mean that okay, I don't understand. So
it's a dynamical principle that explains why mathematicians tend to develop theories that stray far from undecidability, right?
Look,
why is that not a valid statement?
I don't know. I don't know because, look, I'm thinking about, we got a multi-way graph, right? Yeah. It's got proofs in it, right?
Yes.
Those are geodesics. Okay. So now, then where do we go? Right. So we got these geodesics, we got bundles of geodesics.
So yeah, I understand the setup, trust me. So okay, maybe it's easier if I explain it this way, right? So imagine a mathematical space in which the weak cosmic censorship conjecture was false. So in other words, you just have naked singularities floating around, right? Mm-hmm. And in other words, you could follow a geodesic path and just end up at an undecidable statement without even realizing that you'd gotten there.
What do we mean by an undecidable statement here?
Well, one that requires an infinite number of proof steps to reach.
All right, so we've got some multi-way graph, right? We got some random multi-way graph, wherever it is, right? Wherever this thing is. Okay, here I've got my favorite random multi-way graph here. Okay, so we can take, yeah.
Hello?
Yes. No.
Can you hear me? Sorry. Yeah. Sorry. We can take.
Yeah. Right. So that's very odd. My power glitched, which is very strange. Hello.
Hello.
Did I lose you there?
Yeah, your audio dropped out for about 30 seconds.
Okay. I think my power somehow, it's very bizarre. This is a perfectly ordinary day, and I think my fine system switched itself over to its generator. How odd. And now wait a minute. It looks like I'm. Can you see my screen or not?
Yeah, I can see your cursor.
But if I go to wolframphysics.org, it's not connecting.
Ah, hang on. It is connecting for me.
Well, I understand, but it's not connecting for me, and it's very odd that my web browser. Well, I'm absolutely amazed that this connection, this Zoom connection, has stayed up, given that just a minute. Let me just text somebody. Okay, in any case, all right, so we've got this random multi-way graph, okay?
Mm-hmm.
And we've got Geodesic through this thing, right? Now, to get to a given, I mean, first thing is there's a slight confusion, which maybe you've untangled, between there's several different things going on here. This thing, this one-way multi-way graph, right?
The implicational versus equational thing, right? Which we've discussed.
I think it's okay. Maybe you've understood it, but it's not quite implicational. It's a little bit different from that.
Well, it could be implicational or it could be semantic entailment, depending on how you set it up. But it's one of the two, I think.
It's not material implication. It avoids material implication. Just confuses the whole thing. It's some other. I don't know what semantic entailment is. I should look that up, but I don't know what that is. So that's is that a thing in intuitionistic logic or what?
It's in ordinary classical logic. It's just, it's logical consequence, but at the higher order than standard implication.
What do you mean? What do you mean? What do you mean by a higher order of what? I mean,
so if you say A implies B, right? That's a purely propositional statement. Whereas if you say A entails B in the semantic entailment sense, then you're still saying if A is true, then B is true. But the entailment symbol, the turnstile, is a symbol in a higher order logic than the one you started with.
Okay, all right. I don't know about that. I mean, I can imagine how that works, but okay. But anyway, so we've got this thing, we got this graph, and it's not obvious to me, right? So these things can be thought of as propositions, presumably, but if we are doing implication-based logic, then our axioms are propositions. But in our case, our axioms are transformations.
Right, because in implications-based logic, you would make a distinction between axioms, which would be the initial conditions, and rules of inference, which are the rules.
Yes.
And in the equational case, there's trivial interconvertibility between the two, which there isn't in the implicational case.
Well, but the rules of inference, usually, in the way people set things up, the rules of inference are fixed and trivial. They're things like modus ponens.
Yeah, right, exactly.
Whereas, but so, I mean, the question is, okay, fine, but all right. So there's a question of how that relates to the equational case, because in the equational case,
Then there's trivial interconvertibility between the axioms and the inference rules. The inference rules are, are derived by paramodulation of the axioms.
What the hell does paramodulation, which is this weird thing with how should I understand paramodulation? My understanding of it is that it's this weird trick with pattern variables and things.
Yeah, it's the thing that allows you to do rule orientation. It's the thing that says if you have an equational axiom of the form A equals B, you can convert it to one that says pattern A goes to B and pattern B goes to A.
Fine.
Right.
Okay.
That's an interconvertibility that exists in equational logic, but not in full, but not in sort of implicational propositional logic.
Okay. But look. So, okay. All right. So then the next claim here, well, still, I'm not completely understanding that. And I also don't understand, if we have a group, for example, right, and we've got its equational, its relations, right? It doesn't have rules of inference. It has relations. An algebraic object like that has relations in it.
Yeah. So
right?
The definition of an algebraic object is one that's defined by equational logic.
Well, I understand. But so you've wanted to expand. So then in that equational setup, each usually thought of as distinct element of the group is a connected component in the multi-way system formed from its equational logic, right?
Uh-huh. Sure.
Okay. Now, in your way of setting up groups in the multi-way group thing, for example, you are imagining that in addition to those equational transformations, those relation transformations, there are additional transformations which basically explore new parts of the group. I don't understand the relationship of those to kind of the logic of what's going on in the group.
Well, if you want to prove an equational theorem about groups, that's exactly what you want.
Is what?
Is the ability to have both generators and relations be, converted to rules in the multi-way system, as well as the underlying axiom.
How do you prove? I mean, the proofs in group theory are proofs that follow relations. They follow the axioms or they follow relations in the group.
Right, but if you want to prove something equationally, then you need the generators as well.
What do you mean? If you want to prove something, equationally,
if I want to prove that,
yeah, go ahead.
If I want to prove that x equals y, subject, within a particular group, then I need to have the ability to multiply x and y, say on the right, by some element g. That's an operation that I need to be able to do.
I don't understand. And most of the results that one we want to prove are of the form, this word equals that word.
Yeah, right, exactly. So in the process of reducing that to a tautology, I need to be able to, in addition to simply applying group relations to both sides, I also need to be able to multiply on both sides. There are situations where I want to multiply by the identity or multiply by the inverse or whatever.
But then in the usual picture of how, like I have all these pictures of getting, your typical theorem, right? This is a typical theorem that is just an equational theorem like this, right?
Yeah.
I don't understand. If I were to add in here a transformation that just adds a symbol to the right-hand side.
Yeah, obviously it wouldn't work in this case because it's non-equational.
But it isn't non-equational. It's an equational logic system. It's an equational...
But it's being proved in a non-equational way.
Why?
Because the equational way of proving it would be to have, P NAND Q equals Q NAND P and then reduce to a tautology.
Wait a minute, wait a minute, wait a minute. We're using the term equational in a different sense. So I mean, one thing we can do is have every at every step have a proposition, right? Everything is a proposition. So then one proposition would be A equals B, right?
Right. That's the definition of equational logic, right? That every proposition is an equation. So in the proof you show opposite. I mean, it's obviously convertible into an equational logic proof, and I can see why you laid it out this way as a simple rewriting system that doesn't have equations in it. But these aren't propositions in equational logic, right? They are simply expressions.
I understand, but then it's not the case that a relation. Look, the way of understanding this for a group, for example, is there's a two-way arrow here, and those represent relations that say this word is equal to this word, don't they? That's different from already having. Okay, so what is the relationship between that and saying A equals B and having every node be of the form A equals B? In this case, what you're saying, what you seem to be saying is, and that's what an equational logic theorem prover typically does, is every node is of the form A equals B.
Exactly.
Right? Okay. Whereas here, and if every node is of that form, this type of multi-way system is doing something a bit different, right? It's taking...
Sure, because its propositions aren't equations.
I know. So you're saying, if you take, for example, your multi-way group, if I have your multi-way group thing, right? Your multi-way group, the elements here are words, correct?
Yeah.
Okay, so if the elements are words, they're not propositions.
No, of course. Yeah. But it only becomes interesting once they are. I mean, that's why it's been developed.
But they're not. I mean, but that's the point, that they're not in the usual way of setting it up. It's not completely uninteresting that even when they're, by the way, is the multi-way group thing published in the function repository or not?
No.
Okay, I can find it though in the Dropbox presumably. Where is it? JG drafts or something else?
It's in JGWIP in code development. Below JGWIP.
What does WIP stand for?
Work in progress.
Okay.
They're still in development.
I was not quick enough to understand that.
Including the equational stuff, which is the next obvious step.
Okay, but so in multi-way group, I don't know whether the examples are valid here. No, there aren't any examples here. Okay, so if I can run this, I mean, I might as well put an example in here unless I'm messing things up by editing this.
No, I was.
Okay, so let me put an example in here. So if I say multi-way group of, what can I say, A, B, what do I do for the connector? Do I use a double arrow or what?
You can, yeah.
Actually, I think I can just use ordinary.
Yep.
Yeah. I don't do that very often. Okay, so this here, so what do I do here? I say multi-way group, and then do I have to give it an initial condition or not?
No, but you do have to give it a set of generators and a set of inverses and an identity.
Okay, so I have to list those in an association.
No, you can just pass them in as lists. There is a shorthand. So if you pass in a list A, B as the first
sublist.
Argument.
A, comma, B.
Yep.
First argument or first sub-argument?
No, first argument. And then after the relations, then you put just say E in inverted commas or something. And then whatever your inverse elements want to be. X and Y or whatever.
Okay,
Yep.
like this. And then a number of steps.
Yep.
And then something like states graph.
Right.
Let's do only 2 steps. Oh, cool. Okay, so let's do the free group first. Okay, let's do 1 step in the free group. What does that mean? So this means, so this line, that is your multiplied by a generator line. Is that correct?
That's what red lines mean.
Okay. So then if I go 2 steps, so presumably I could just do the 1 generator free group, right? Not very exciting, but the 1 generator free group. And let's go 3 steps with that. Oh my God, that's already so complicated. Okay, so let's take a look at this. So this is saying, what are the 3 colors of lines?
Yeah, so for context, the red arrows are applications of generators. The blue lines, if I recall, or the light blue lines, if I recall correctly, are applications of the underlying group axioms.
Okay, so the cyan are group axioms.
Or no, actually, I may have color coded it even more closely than that. No, actually, yeah. I think I picked individual colors for different group axioms. Let me just check.
That's the identity.
Yeah. Okay, so generators are in red, relations are in green, identity is cyan, inverse is a magenta, and commutativity, which you don't have enabled right now, is blue. But if you want to, you could make this group commutative if you wanted to.
Okay, so green is the actual group relations.
Yep.
Okay.
Yeah, so cyan is application of the identity axiom, and magenta is application of the inverse axiom. There's no reason for these colors. It's just...
Yeah, okay, I can probably figure out some better colors. But okay, all right, so that's those. All right, so now the vast majority of the stuff that's going on here is multiplying by generators.
Yep, and if you want to, you can run that with append only true. If you want to see your prunes down version.
Okay, so this will be the free group on 1. What the hell does this do? So you're saying if I go states graph structure, why is this showing me the free group on 1 element? Is that obvious? So the free group, so your red things should correspond to the things which would be pieces of a Cayley graph. And these things here are the modding down, are the things that show equivalence classes, right?
Yeah, except there's some subtlety because, of course, the Cayley graph doesn't, in this case, the red also shows, multiplication by identity or inverse, which wouldn't be shown in the Cayley graph. That's probably an argument to have an additional layer of coloration within the reds to show which are multiplications by generators specifically, and which are multiplications by other random group elements.
Right.
But yeah, if you only showed the,
right, not only multiplication by generators, but also by E, etc. Okay, so if I were to do here, if I were to take this and I were to add some random thing I were to say AA goes to A, for example, a cyclic thingy,
Right.
then I would start seeing a few, let's do it for 3 steps. My God, this is so complicated. Okay, so that, as compared to the free version of that.
And so in particular, you can start proving theorems with this, right? Because, so but by saying AA goes to A, you are implicitly saying that big A equals little a, right? Oh, no, you're not. No, sorry. No, never mind.
Well, I could also do a relation that says big A and little a are the same.
No, I'm thinking if you did, if you did if you did AA goes, oh, that's interesting.
So that means the element AA is self-inverse.
Yeah, but what I was wondering was if you say AA goes to E, then that's another way of saying A goes to little a, big A goes to little a. But then you should be able to find a path from big A to little a and back again, which you wouldn't have been able to find in the original graph. So that, you know, that's the sense in which this structure allows you to kind of prove equational theorems.
Okay, hold on. So the nodes here are words. Let's remind ourselves, the nodes are words. And some edges here are just exploratory edges, but some edges are theorem edges, basically, which is quite confusing, right? I mean, in what sense? Okay, but what is the relationship between this and the thing equals thing version of this graph? Did you get what I'm saying?
Yeah, it's the same, except that you apply everything to both sides rather than just one expression.
But in what sense? What do you mean it's the same? I mean, here you've proven a theorem by walking from one node to another, right? As opposed to in the other case, where you prove a theorem by walking from a node that is a propositional node to the node that means true.
Yeah, right.
But that's different from what you're doing here. What you're doing here is you're walking from node to node where every node is a word.
Yeah, I know. I know what's going on.
But some things here, some paths here are not theorems. The red paths here are not theorems. The green paths are theorems, the red paths are not.
Right.
So this is why I'm confused. Because normally in this word-based network, I would think that every path is a theorem. Right? Whereas the alternative is a theorem is something which connects to the true proposition node.
Yeah.
Right? Which is more like what happens in a theorem prover.
Mm-hmm.
Okay, so just can you compare those two ideas? Because I don't understand the comparison. I understand the case where it's word to word to word, transformed by relations, which is what you're showing in the green subgraph here, right? I don't understand what this graph is. This graph is a combination, it seems to me, of two types of graphs.
Yeah.
So can you explain, look, the two cases are, there's, case one is, every node is a proposition. A true theorem is a path from a proposition node
to a tautology.
Yeah, from a proposition node to the true node, right? The single node that means true. Is that correct?
Yeah, or to a tautology.
Well, but that which tautology is then equivalent to that node that says true, right?
Right.
There aren't multiple tautologies. They're all equivalent to that true node. Okay, so case 2 is every node is a word, and theorems are paths between equivalent words. Okay. Now, which of those is this? It's a mixture between those, isn't it?
Yeah, I mean, because it's not an equational version. Yeah, it's neither.
Okay, but what is it? Right? In other words, how do I understand? How do I read something off from this? How do I read off theorems of mathematics from this? Are they only in the green?
Yeah. Well, not necessarily in the green. They're in everything other than the red. Or more precisely,
Yeah,
I mean, yeah, sorry.
Yeah, okay, fair enough. But so what is the role of the red edges here in, what is this model?
Populate the set of possible propositions.
Fine. I understand that. But what is that? That is not, in the traditional view of sort of the progress of mathematics, that isn't, if I take my picture from Euclid, right, that's not what that is.
No, because Euclid was working with a fixed set of things that he wanted to do, right? Red is the exploratory progress of mathematics, and everything else is the proving of theorems within that framework.
Yeah, but okay. So if we take this in the physics analogy,
this is combining the processes of conjecturing and proving.
Yeah.
Right.
Okay. Fair enough.
Which the other thing you're proposing would not be doing. It would only be proving.
Fine. Okay. Then at least I understand it. Okay. So now let's look at the analogy between this and what happens in physics. Right? I mean, in physics, well, okay, so what's the analogy between this expansion of the metamathematical universe, so to speak? Look, the multi-way systems that we're looking at in physics, why are they analogous to, I mean, we can think of them as defining, as corresponding to relations and things. Okay, I don't understand. It seems very arbitrary to put in this sort of your, conjecture network on top of the proof network. Why is it not arbitrary? I mean, is there an argument that this is closer?
I don't understand. I mean, there's in physics we have evolution and we have measurement. Those are both aspects of the physical universe, aren't they?
Well, there's in your idea about measurement as okay. So hold on. There's presumably, in this model, the red is completely free. It's just treeing everything out, right?
Right.
Okay. So that doesn't contain much dynamics. The dynamics is in the mixture of that and the relations.
Mm-hmm.
Okay, but I don't understand why. I don't understand why this is a good correspondence with physics. I don't get it. I don't get why. I mean, to my mind, what I'm suspecting and what I, basically was arguing in the NKS case is that straight multi-way systems are a decent model for the progress of mathematics in the sense that what it is doing is to say this is equal to that. Maybe across very big, maybe on long geodesics, right? Large distances. But I don't get why I just don't get this. I'm sorry, I don't get this. Maybe I'm
Okay. What's the question?
well, I'm trying to understand your statement. Okay, so in the ordinary multi-way graph, there are geodesics that correspond to proofs. Okay. Here, there are geodesics that do not correspond to proofs. There are geodesics that correspond.
Oh, they correspond to proofs if one of the axioms is you can multiply by generators.
But that's not a model. That's not a reasonable model for mathematics as people do it, is it? That's not an axiom. I mean, it's not something that's like saying you're going off and exploring a different thing. It's not like saying,
yeah, like I say, it's combining both conjecturing and proving. That was the whole point.
Yeah, but it's no longer maintaining truth, right? If you have an axiom that says, and you can go off and do this completely different thing, that axiom, the point of axioms is to make statements of things which you believe to be true. The fact that,
sure.
But this isn't doing that. This is something different.
No, but it is, right? If you are constraining yourself only to follow edges that are non-generator edges.
Well, I understand, but I'm saying, yes, right. So you've got two
which
different
I think is
networks.
a reasonable model.
But you've got two different networks going on here. You've got, I'm not sure it's a reasonable model. I think it's a much simpler model to just say that all that's happening is you're following a multi-way graph. And that the true facts of mathematics are the connections between one node here and another node here. That you're modeling.
But the metamathematical multi-way graph is a Rulio multi-way graph, which doesn't, quote, maintain truth either. Everything is connected in the multi-way graph for all possible rules, because it contains all possible axiomizations. What you have to do is construct a fibration, which is exactly what I'm proposing you do here.
Okay, so there is a Rulio version of this, right? In which you have all possible axiom systems, right? And in which it's not that exciting because everything is, in that Rulio system, everything is connected to everything.
Right.
I agree.
And so it's useful because it combines both the conjectural and proving aspects of metamathematics. So then if you construct a vibration that corresponds to a particular choice of axiomatization, then it ceases to be a construction of metamathematics and it becomes a construction of mathematics.
Well, I don't know. I think that's a different definition of, I mean, metamathematics, it depends what you mean by, there's Rulio metamathematics. There's the space of all possible axiom systems of metamathematics, which is different from what Gödel would have meant by metamathematics.
Well, no, this is a more general version, right? But
it's metamathematics, right? But so
that's why in the bulletin I use this phrase pre-mathematics rather than metamathematics as being the structure from which the structure of mathematics derives.
Okay, fair enough. But yeah, all right, fair enough. But then the question is, okay, so we've got a mathematical, whatever it is, we got a multi-way graph which corresponds to a field of mathematics. Mm-hmm. You can think of it as a fibration of the Rulio multi-way graph of all possible axiom systems.
Yep.
Okay, I don't really understand your thing about having generators mixed with relations. I don't understand that, but whatever, maybe it isn't important, I don't know. But then the question is, within this multi-way graph that represents a piece of a field of mathematics, then we can ask questions like, we look at a bundle of geodesics in that graph, right? And now, for example, in that graph, we could, okay, what is the significance of the causal edges in that graph? in a graph like this?
You mean beyond abstraction?
Well, I'm not. Yes. What is the more simple-minded significance? In other words, so for example, one thing we could do is we could say, you know, we could invent, we could add a sort of a weird time-like kind of completion, right? We could say, let's add in this theorem, the theorem A equals AAB, right? If we add in that theorem, we will change this multi-way graph.
Yeah.
So one question would be how to think about those added in theorems. In other words, are there theorems that, for example, have high leverage? They take you a long way and they're useful, as opposed to theorems that just, you know, expand a prong, so to speak. Do you have a way to think about those?
Well, in the meta-mathematical case, yeah.
What do you mean, the meta? You mean the pre-mathematical or the meta or some other meta-mathematical?
I mean, no, yeah, I mean, in the case I discussed in the bulletin, right, that these load-bearing lemmas, as I think I described them, those are just things that have higher than average vertex connectivity in the associated proof graph.
Is this a proof graph or is this not a proof graph?
You can think of it as a composition of several proof graphs.
Well, you're saying, I see, but by proof graph, you mean a proof graph of the kind that the theorem prover makes.
Yeah.
Okay, but in this case, because these are not propositions, in the theorem prover, every node is a proposition, right? These are not propositions, these are words.
Okay, only because you're choosing to call them that. There's also a perfectly valid interpretation of them in terms of propositions.
Well, not with one-way edges.
Sure, with one-way edges.
Look, in the theorem prover, it goes both ways.
Because it's equational logic.
Right.
Which this is not. But there are other propositions beyond equational ones.
Fine. Which the theorem prover is not set up to deal with.
Well, it is now. It is in version 12. That's the whole predicate logic thing that I set up, right?
How can we use that?
For what?
Well, to make a picture like this one, as opposed to, so when you do a predicate logic proof, it still looks the same as an equational proof, right?
Right, because it's converting it into, the proof is equational, even though the theorem is predicate. But the point is, it doesn't have to be two-way.
Well, the edges...
You can define asymmetric rules of inference.
But the edges are still two-way in the proof graph, right?
Because it's being converted to equational logic and then proved, yeah.
Okay. But okay.
In effect, the prover is making use of the fact. I mean, obviously, I didn't think of it like this at the time. It's a standard technique of, you scholarize the first order logic expression, you convert it into one that's equational. Implicitly, what that's the reason why that works, and I think this is kind of cool, is it's exploiting the fact that the rule system has a topos structure, and so you can localize.
Okay.
Right. The reason why that scholarization procedure works is precisely because you can convert morphisms to isomorphisms locally, which I hadn't really appreciated before.
Yeah. Okay.
That's
nice. Right. Okay. But here. Okay, the question is, if we were to pull out one proof from this, right? What would the theorem prover's version of this look like? And what would the okay, when we have the causal graph from this, well, okay, okay, we've got a single path here, but the theorem prover would not give us a single path. It would give us something more complicated than that. Why?
Because there are bifurcations. So in order for you to unambiguously specify which path to follow, you have to impose rules that say, those bifurcations are equivalent. So you get the critical pair triangles.
Okay, but I don't understand. If I were to pick a particular, so if I have, I mean, this you've got to find. Is find string proof in the function repository or not yet?
Yep. Yeah.
Okay, so if I say find string proof. Okay, so now how do I write it out?
So you would say A goes to whatever as the first argument. You would say A goes to whatever.
I'd say A goes to AABA. Okay, and then the
Yep.
axioms. Yes, like this.
Yep.
Okay, and then I say okay. All right. So now, is there a way to label this by any chance?
It's already got tooltips.
Is there any way to display the tooltips? I mean, I'm sure I could just write a thing that will make each tooltip be. Is there a way to visibilize the tooltips?
I don't know.
Okay. Let me see if there's. Just hold on a second. Let me just look at the input form of this. Okay, so those are in annotation rules. Oh, so if I just take the annotation rules out of this, and then I take each one of those and I make the tooltip into a vertex label, it should work, I think. Okay, so if I say annotate, do you know how to get annotation rules out of one of these things?
No. Graph of vertex labels goes to that.
That won't quite work because it has tooltips in it. I have to get rid of the tooltips.
Yeah.
Okay, there we go. Okay, I could probably get rid of the. Actually, I could get rid of the. I could just give the right hand side there. So I could take this sub. I think that's a column, so that's a sub 1, sub 2. There we go. Okay, there we have it. All right. All right, so let's understand what this did now. Okay, so this is saying, this is going from A, B, A equals A, right? That's the thing I was trying to prove, right? And these are now, so I don't quite understand. Oh, let's see, there's the associativity axiom. There's the axiom, there's the associativity axiom. Those are the equational versions of the transformation rules, which are bizarrely backwards relative to this, right? Am I making sense?
Yeah. I know how the proof graph works.
Well, I know, but why is it reversing these? Is there a good reason why it reversed those?
Why does it matter? They're all equational.
Well, because it isn't, in fact, representing this picture. It's representing the equational version of this picture, correct?
Mm-hmm. Right.
Where it could go up and back down again, right? So, so in other words, even though here AA goes to AAA, in ABA, what's the relationship between causal invariance and the fact that, and being able to make this two-way? Is there a relationship between those things?
I mean, not an immediate one that I could. I mean, obviously, they are related, but there's no immediate direction of implication.
Okay, so then here, let's look at what this is trying to do. So this is trying to say ABA equals A, right? So how does it do that? So how does this picture relate to the path in this graph? So AA equals, A goes to AABA would be a path in here, right? So it's with, so I could say highlight graph Okay, so there's my graph, my subgraph here. Now, what's the relationship between that path and this proof here?
Well, there isn't a direct one because one is equational and one is not. But assuming that they were comparable, then that path would be precisely the sequence of substitution lemmas, with the critical pair lemmas indicating points of bifurcation and hence of potential ambiguity in the updating order.
But every one of these, so I could make this if I wanted to. I could make this an equational. Look, how I could make this equational by just saying AB goes to A, BB goes to A, right?
A goes to BB.
A goes to BB, yeah. Why is this showing, why is the shortest path here going both ways. Oh,
You
it's
said highlight graph, subgraph,
subgraph, yeah.
and path graph produces an undirected, sorry, a one-way directed thing.
I would say directed graph here. Is that right? Directed edges, I think is the right term. Oh, I don't know why this isn't working. But okay, in any case, I get the idea. Okay, so now I've got an equational version of this, correct?
Mm-hmm.
Okay, so now what's the analogy between this and this?
Well, now they are the same, right? You can see the rewrite sequence happening on the left-hand side.
Okay, let's see it. So this is,
you know, ABBA goes to ABA goes to AA goes to A, for instance.
sorry,
Four steps.
Sorry, hold on a second. So from true, where do I mean, it should be AB. That's AA goes to A. I don't understand that. That's somewhere here. Where is AA goes to A?
AA is in that sequence.
It's in the sequence here, right?
Yeah.
But why this sequence is a different order from this sequence? Is that surprising?
No, because it's allowed to use substitution lemmas, which the other sequence is not.
Okay. What is a substitution lemma in this picture? Is it not just something that says that it is a jump ahead, so to speak?
Yeah,
one
exactly.
of these
This is what we were discussing earlier.
Okay, so how does it make the substitution lemmas from here? So in other words, where do you see, okay, so here we've got A, B, 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 I don't know what the X, oh, that's just a different thing, okay. A, B, 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 something or other. Is somewhere, I don't understand. So it made a longer thing here in the middle. What do the dashed lines? What is the analog of the dashed lines? So substitution lemma. What's that?
Causal edges.
Why? What is a substitution lemma? A substitution lemma is, okay, if I'm trying to make an analogy between this picture and this picture, what am I doing? How do I make that correspondence?
Well, the substitution lemmas are the states. The critical pair lemmas are indications of elementary bifurcations. The dashed lines are the causal edges. The green lines are the initial conditions. So.
Okay. In particular, in this case, what am I doing? In particular, it's A, B, 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 A equals A. Where does that show up here?
Well, there's the state ABBA corresponding to that state.
Okay, so A, B, B, A, A, B, 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 A, wherever it is.
ABBA was the state you just indicated.
Okay.
Which is next to AABB in that graph.
Okay, it's here. It's a state here, right? That one there. Okay, so you're saying that that lemma is equivalent to the is adding a direct arrow from A to ABBA, right?
Yeah.
So we can think of that lemma as being an additional connection made there. Okay, so the relationship from one lemma to another is by applying some arrow that already exists, right?
Yep.
Okay, so in this picture, the creation of new arrows is going down the page, correct?
Yep.
Okay, so
look, I mean, it's really, I don't know, maybe it's just, I think this is really simple, right? All it's doing is it's taking the multi-way evolution graph and it's computing a transitive closure, just like I said in the bulletin. I don't see why this is complicated.
What do you mean it's computing? It's each one of these, right?
In the multi-way evolution graph, every time I go from state A to state B to state C, I'm saying, well, now there's a shortcut, so I could just go directly from A to C. I don't have to go
I
through
understand
B.
that. I understand that. If you can
which
find
is a transitive closure.
Yes, that's right.
So, like, what? Yeah, as I think I said in the bulletin. So I just don't. What's the question here?
Okay,
that's the connection, right?
No, every node here, right? Every node
is a state node.
It's not a state node because the transitive closure is a bunch of arrows here.
Yeah.
Right? So it's not the same as this node is equivalent to an arrow up here, right?
Is equivalent to an event, yeah.
Right. And the arrow here between two events.
Well, no, that was the point, right? There are events, and then there are states that those events produce, and in the proof graph they are conflated, so so each node can be treated either as an event or the state that it induces. But that's okay because the solid lines are the evolution edges and the dashed lines are the causal edges. So you still make a distinction between the two.
I'm sorry, could you run that by me one more time? Look, I understand you can get, you can take some random piece of this, right? We could take some random small piece of this, right? And we can make, okay, take this thing and take it just for a couple of steps, 3 steps or something. And now we can say transitive closure graph. Right, that's the set of all possible theorems. We've turned every theorem into a one-step proof here, right?
Yeah.
In this picture, right? Okay, so we are now selecting from those one-step proofs to get our substitution lemmas here, right?
Yeah.
As well as these lemmas, right? Those are also, no, those are not.
Those are indications of elementary bifurcations.
Yes, but those will also occur in the transitive closure. Do those also occur? They do, don't they?
They occur on space-like slices rather than time-like separations. Yes.
Well, do they have arrows between them or not?
No, they occur on space-like slices rather than time-like separations.
Right. So they are, for example, if this didn't have otherwise have an arrow between it, in this picture, for example,
AA and ABBB are space-like separated.
Right, but nevertheless, both in an equational system, both follow.
Yeah.
In another system, they would not follow, but in an equational system, they do both follow. Right. So. So every node here corresponds to an event.
And a state.
Why a state?
Because events output states.
All right. And then the lines joining these.
The solid lines are evolution edges between states, and the dashed lines are causal edges between events.
Explain that. Why is this a causal edge between? Because this now is an elementary bifurcation there, right? That thing is a bifurcation.
Yeah. Well, let's talk about the substitution lemma case first, because I think that's simpler.
Okay. Well, where do we have an example of that going on here? In this case here, for example, A, B, this one here, is that an example of one where there's a dashed line?
Or the A equals AA and AA equals A pair.
Where is that?
The final two before the true.
Which one? Sorry, this?
Yeah, the final two before the true. A equals AA and AA equals A.
Okay, those two. All right, okay. So, okay, so explain this one here. So this
Right.
is...
So the state AA is evolving to the state A, hence the solid line on the left. Right?
I don't understand. Where's it evolving? Solid line from what to what?
From AA to A.
There's no solid line from AA to A. This is a solid line.
There is.
Where?
The reason it's reducing to true is because the AA on the left-hand side is reducing to A.
I understand that. I understand that. Okay. Yes. Yes.
Okay. So that's an evolution between two states, AA and A.
Yes.
But the reason why that event is able to occur is because the event that led to the state A equals AA had previously occurred, from which the resultant rule that allowed you to map AA to A was derived.
Oh God, I don't understand. Are you describing this edge here, or are you describing a different edge?
Yeah, it's a causal edge, right? It's saying this event, the event on the left couldn't have been applied unless the event on the right had previously been applied.
But why isn't that causal edge then? Why isn't this causal edge leading to this event here?
Because that's not that event that's dependent on it. It's the event that yields true that is dependent on it.
Okay, so there's really an event here. So it's a little bit refactored. This picture is a little bit refactored.
Well, like I said, every node is both a state and the event that yielded that state. But that's okay because you make a separation between the evolution edges and the causal edges, so there's no information lost.
But there's a way of drawing this picture in which we could show explicitly the states and the events. Like this thing here, this thing is
a state and an event that led to it. We could draw them separately, but we don't.
Okay, but it's the, well, but when it comes in like this, that is a causal edge going to the event.
Right.
This is an
evolution edge between two states. Yeah.
Okay, and the state is then the destination state is AA here.
Right.
And the destination event is AA goes to A. Right? The destination event for this causal edge is AA goes to A.
No. No, I don't understand. The event is BA goes to A.
Here? Where do you see the B?
Because that's the event that got applied.
How do you know?
You can see it, right? That's
where?
ABA goes to AA.
I'm sorry, what are you looking at? I'm looking at this edge here.
Yes.
Okay, where's the B involved with that edge?
Well, in the left-hand side of the critical pair lemma, but more importantly, you can see it from the evolution edge.
Which evolution edge? This one here?
Yeah.
Oh gosh, this is confusing. All right.
State ABA evolves to state A. In doing so, it makes use of the that event. Okay, so
this event here, right? This event here, which would otherwise be drawn as the right-hand side of this transformation, is where? So if we were normally drawing it with states and events, which will be the state and which will be the event here?
The state is ABA, and the event is the event that yielded it, which in that case is BA goes to A again.
From another state? From this state here?
Well, events connect states, yeah, that's how it works.
Okay, but I know. But you're saying, look, this picture, right? So what you're saying is, if I took this picture, right? Okay, so every substitution of the form x equals y could be broken. So every substitution should get, is it correct that every substitution has a causal edge and a state edge coming into it, an evolution edge coming into it?
Yes, because in equational logic, every object is both a proposition and and an event.
Okay, has an evolution edge and a causal edge. Okay, and the evolution edge is saying, okay, so where's the causal edge coming from in this picture? Where does the causal edge, what if I drew the causal edges from this picture, would they be the same causal edges as in here or not?
No, because that's not a transitive reduction graph, a transitive closure graph.
Okay, fine. So let's imagine that I did the transitive closure, right? So after transitive closure, then if I were to do this transitive closure, and then how would I do that? How would I draw the causal edges for this transitive closure? Well, it's easy enough to do. I just add in all those additional events. After transitive closure, the causal edges in the proof graph are the same as from the other thing. Okay, so you're saying that this, but because it's equational logic, you can add in these critical pair lemmas, and because it's got the two-way thing going on, you can add those in. All right, but okay, so yeah. All right, so we were talking about geodesics before we got distracted into all of this. I mean, we're saying that these are, I'm a little bit confused by the role of geodesics in these transitive closure graphs, because it seems like you're always going in one step. You can always get from anywhere to anywhere in a transitive closure graph.
Yeah.
So what is a geodesic in that case?
What I mean, the geodesic is the sequences of edges that makes up the closure. Of course, it's the case that once you've proved a theorem, you can reprove it in a single step. Right?
Okay, but so
the whole point.
Right, but the geodesic. So this thing here is not a useful thing to look at when you're looking at geodesics, because it has already had a bunch of.
No, it's the most useful thing, right? Because it's a geodesic, but with all of the extraneous information removed.
But it hasn't been, because it's using. It's making use of substitution lemmas. In this particular case, it isn't particularly, but it could be making use of substitution lemmas, which represent, multi-step jumps from before.
Right. Yeah.
Right?
So
Whereas,
it's stripping out the extraneous information.
Well, I don't know whether you call that extraneous, but it is speeding it up by some amount, right? Because it would take it longer to go through the full multi-way graph here.
Well, yeah, and that's the point of proving lemmas.
Indeed. But so, okay, so okay, geodesics in here have certain properties. which may or may not be preserved when you get to this thing. Now, the claim is, I mean, what is your claim about geodesics in here? Or is it a claim about geodesics in here? I'm totally confused.
Well, I'm confused as well. So I mean, the claim I made in the bulletin, I thought was quite clear. It's that you're just doing homotopes between paths.
What's doing homotopes between paths?
The translation between a proof graph and a multi-way graph, or path and a multi-way graph.
No, that sounds about right. But
right, because the whole point is that the proof graph is stripping away intermediate information, but between pairs of states, because you're proving substitution lemmas. But the topological information is still there. You're just doing a smooth transformation between two paths.
Well, except there isn't a lot of topological information because there's only one path here.
No, but there's topological information in the multi-way system.
In here, there's topological information, but it has been stripped out because you're looking at just a single path in the proof graph.
But its presence is still there. I mean, which is why you have critical pair lemmas. You have non-trivial holonomies there.
That's true. All right. Okay. Fair point. Okay. So then, but what is your claim then about, so if I were to look at a geodesic in here, and your basic claim is if there were no, I mean, a bundle of geodesics here would just not interfere with each other at all if there were no critical pair lemmas.
Right. In the absence of any topological obstructions, I can stretch and scale paths as I like, which is why I can prove substitution lemmas and use them to shorten future proofs. The place where that gets complicated if there are topological obstructions, if there are non-trivial holonomies and things. That's why you have to prove critical pair lemmas to take care of that.
Right. Okay, I understand. But in that case, what we're saying is we have a bundle of geodesics. And what do we claim is true about that bundle of geodesics? Okay, what is the mathematical analog? I mean, okay, so in the physics case, we expect that there's a relationship between the sort of straightness of the geodesic and the presence of causal edges.
Yep.
Right. And the claim is that the same is true here.
Yep. As I gave an explicit example of.
I better look at your example. What's the example?
Oh, the higher the density of non-trivial holonomies, the more the geodesic divergence as a consequence of perturbation in the proof graph. It's in the relativistic interpretation section. I think I showed two proof graphs next to each other that have this property.
Oh yeah, I think were those the two proof graphs we worked out where you jump this one here?
Right.
Right.
So I make an infinitesimal perturbation to one of the geodesics, and then show that the resultant effect is more than just one. Whereas in the case which is why we can say this is a curved space. Whereas in the example I gave before that, where you have a flat space, perturbation of order 1 produces a change in the geodesic length of order 1, just before that. There you go. So there are no non-trivial holonomies there. And then I even show, if you look below, how that relates to the evolution causal graph. Which section are you in? Yeah, just below there. in the, I don't know, the bit with the evolution causal graph. Anyway, I demonstrate how the proof graph is just an evolution causal graph, just with different encoding.
You know, just as a market study, okay, my inability to understand this stuff quickly is not a great market size indicator.
Right.
And but okay, we looked at this like 2 weeks ago, right? This particular thing. I understand. This is what you get when you add an additional, there's the additional, initial axiom, so to speak. I don't know, the additional, yes, that was an additional axiom, right? To perturb this thing. Okay, then the question is, what is the large scale interpretation of this?
Yeah.
Right, what does this tell you?
Well, so as I say in this section, right, it's that there's a direct relationship between the abstraction tensor and the density of critical pair lemmas.
Yes, we talked about that. Right, but I'm just not, I don't know. I mean, it's close, but I don't get the details of this. I'm sorry. I mean, I understand in general terms, but I don't get the details. I don't get, and very likely, but I also don't quite get what the overall significance is. Right? I'm trying to understand what, if I look at mathematics as it's been developing, so to speak, and I try to, work out I don't know. Do you think you understand what the implication of this is for kind of the sort of large scale story of mathematics?
Well, as I've been saying,
opposed to meta mathematics, just one level meta mathematics.
As I've been saying, I think the fact that it explains why undecidability is so rare. I think that's a non-trivial. I mean, maybe you think that's obvious, but I don't think it's obvious.
No, and I don't know why it's. Okay. Why do you think it explains why undecidability is rare?
Like I said, it's the geodesic equation plus weak cosmic censorship. Right?
Well, your claim is, let's unpack that, okay? Your claim is undecidability happens when these proofs get arbitrarily long, right?
Yeah.
Okay. So what will make a proof in this picture? Why does a proof not get arbitrarily long? Why does a proof, what is the reason? I mean, there's ultimately, if it's true, there's a sort of essentially combinatorial reason that a proof doesn't get arbitrarily long.
If what's true?
If it is true that what you're basically claiming, that for some reason in metamathematics, as it is enhanced by theorem proving, that is, by making use of essentially jump ahead lemmas, right? You're claiming that the presence that
but that's not a combinatorial. There's not a combinatorial argument. I mean, the statement is still there that infinite length paths can exist.
I understand, but you're saying that the presence, that there are enough jump ahead lemmas that.
That's not my claim.
Okay, what is your claim?
My claim is that of the geodesic equation, right?
Okay, well, explain that, because I don't understand that.
Well, okay, so as I was trying to explain whatever it was an hour and a half ago, so if you could imagine a mathematical space in which you had bare singularities, in which the weak cosmic censorship conjecture was false.
Okay, right? What is a singularity in this situation?
Well, an undecidable statement.
No, but an undecidable statement is an infinite length path. that's not the same as a singularity. That's not the same as, for example, a causal, you know, a disconnection in the causal graph, for example. But, there's different kinds of singularities. There's a time-like singularity, space-like singularity, whatever. They're different. What do you mean? A singularity, having an infinite length path, is not the same thing as, by an infinite length path, you mean there is a proposition that can be reached but only after an infinite length, or you mean there's something disconnected, or what do you mean?
No, I mean an infinite length path. I mean there's a proposition that can only be reached by a path that has length of that is infinite.
Well, which will show up in our pictures as a disconnected piece. True?
If the weak cosmic censorship conjecture is true, which is why I prefaced it by saying, imagine the weak cosmic censorship conjecture was false.
I don't understand that comment. I don't understand that you're saying that okay, so first point is an undecidable proposition in this picture is something not connected, not provable. There's no connected path that we can find to that proposition. There's no path we can find. There's no proof we can find to get to that proposition, right?
Right, but it can still be connected to everything else if the weak cosmic censorship conjecture is false.
Why?
Because the path could just be infinite length.
Fine. What does that have to do with cosmic censorship?
The statement that it's infinite length and therefore disconnects is the statement of weak cosmic censorship, right?
Explain.
But there's nothing to explain. We've defined a singularity. You're then saying, oh, therefore it implies causal disconnection, i.e. an event horizon.
No, there's a singularity is a different thing. A singularity, what do you mean by a singularity? You mean a curvature singularity?
No, I mean a singularity is in a place where your time-like paths become infinite.
Okay, look. As I understand the cosmic censorship thing, you're not talking about curvature in any way. You're simply talking about lengths of time-like paths. Is that right?
Right now, yeah.
Oh, boy. Maybe you have fully understood this. I don't think so. I think there's more to understand here. I don't think, maybe I'm wrong.
I haven't even explained what okay, never mind.
Go ahead, explain.
Okay, so, imagine a mathematical space in which the weak cosmic censorship conjecture is false. So now it's possible for you to hit upon undecidable statements with infinite time-like paths, just like infinite time-like paths exist for singularities in ordinary general relativity, without hitting an event horizon first. Right, without there being effectively any discernible effect on curvature as a consequence of that, that undecidable proposition being there.
Mm-hmm.
That is a version of mathematics in which people would expect to hit upon undecidable statements all the time. The point is that, as far as we can tell, that statement is false, and the reason it's false is because of these generalized Einstein equations that enforce a weak cosmic censorship conjecture. So in particular, in the vicinity of an undecidable proposition, there will be a non-trivial effect on curvature that will deflect geodesics in such a way that the shortest path through this mathematical space, which is what we assume mathematicians are following, i.e. that mathematics evolves according to a geodesic equation, will tend to avoid, regions, not just will they tend to avoid undecidable propositions, but they will also tend to avoid propositions that are in the vicinity of undecidable propositions.
Right, okay, so let's peel that back a bit, okay? So you're saying, assume mathematics progresses through shortest proofs, effectively, right? That it gets to wherever it's going to get to by more or less the shortest proof. That is following a geodesic, right?
Yeah.
Yes?
Yeah.
Okay. Now what you're saying is that if it is doing that, then
there's an
you're saying that
describes mathematics.
What's that?
Then there is an action principle that describes mathematics. And that action principle is a geodesic equation. And if that is true, it means that mathematics will naturally avoid regions in which regions of mathematical space in which the curvature is high, and therefore will tend to avoid undecidable propositions.
Right, but that is essentially, if it's true, that is ultimately that is a statement. If you think about what is underneath that statement, right, it's ultimately going to be essentially a combinatorial statement, because it's a statement about, it has nothing to do with, there's no physics here. It's just a statement about what happens when you make, structures of this kind, right? It's an almost not tautological, but it's a formally following statement. It just says, if you follow geodesics, then those geodesics, a geodesic won't wind itself up in a singularity, which I don't really quite understand. I don't understand. I mean, that will. I'm sorry. I really just don't get this completely. I get roughly. I think roughly it's correct, but I don't get it more precisely. I just don't get how I don't get how to connect these dots. The statement that, all of these statements seem intuitively reasonable, and I can see that structurally you can get there, but I don't see how it works in more detail. I mean, I don't see how you get. You're exploring this metamathematical space by following a geodesic. Fine. Okay. The metamathematical space has a certain structure that is determined by a bunch of geodesics and other things, right? It has a structure that is determined by the underlying rules that were put into this multi-way system, right? Mm-hmm. But now you're saying that these geodesics are for the same reason as in quantum mechanics, deflected by the presence of causal edges, you say. Mm-hmm. Right? Why don't the geodesics why don't they fall into black holes?
Well, okay, so okay, perhaps this is a cleaner way of thinking about it. Imagine the co-version of what I said. So, which would be closer to the original formulation of the Penrose-Hawking singularity theorems, right? So all decidable propositions correspond to inextendable time-like curves, i.e. to singularities, right?
Yeah, they terminate.
Right.
Yeah.
Except that's the explanation. I was trying to go for a time-like version, but if you want to think about it in a space-like case,
wait. You're saying, okay, a geodesic that establishes a decidable theorem is a finite length geodesic. That's what it means to be a decidable proposition. It has a finite proof.
Yeah, so it's a time-like path that's not future extendable, which would be the definition of a space-like singularity. Before I was thinking of time-like singularities because I thought that was easier to understand, but maybe you're saying space-like singularities are easier to understand. So if we take the standard definition of a space-like singularity, region beyond which you have a time-like path that's not future extendable, those are decidable propositions. So then again, the geodesic equation tells us we will tend to stay within the realm of decidability because the weak cosmic censorship conjecture is true. That once you're in the vicinity of decidability, you don't really get out.
This isn't the right view. I mean, look, metamathematics doesn't stop. It doesn't stop. Yes, you can get to a particular point, but you don't get the situation where it stops and there's nothing. That's the end of mathematics, right? Is one of these space-like singularities. That will be an end of mathematics.
No, it wouldn't be. It would be a theorem.
No, a theorem is the ability to get from one point here to another point here. That's the theorem, isn't it? Is just the choice to go from London to New York or something. That's like a theorem. It's the choice to go from one place to another, not that you get stuck somewhere.
Right.
Right? Getting stuck somewhere is an end to that piece of mathematics. There's nowhere else to go. Look, the way I would view a theorem in this mathematical space is a theorem is, you can get from somewhere to somewhere. There is no, you are getting from somewhere to somewhere. You successfully get, and in time, you successfully get from somewhere to somewhere. So an example of a non-theorem.
No, look, again, trust me, I do understand the interpretation of theorems as time-like paths. My point is that these space-like singularities are ones where those time-like paths are not, they terminate at a finite.
I understand that, but that means that you've finished. You've figured out all the theorems in a sense. You cannot go any further in that direction.
In that particular direction, but not in that particular field of mathematics. The field of mathematics, of course, being defined by a vibration.
Yeah, it's the field of mathematics is the whole multi-way graph. Right, but I don't think it's right to interpret a thing where you get stuck in going in a particular direction. I don't think that's quite right. I don't think it's not that every theorem has a black hole associated with it, which is what you're basically saying.
No, not every. I didn't say every theorem. I said the black hole. When reaching the black hole, that is a theorem.
Among many other theorems. I mean, among any other place you could visit.
It's a decidable one. But if you didn't have these, then there would exist you would expect to see many undecidable propositions.
Why? I mean, the fact that there's a path.
Because if I just pick an arbitrary point in space-time,
yes,
then what is it that guarantees that the time-like path from where I am to that point is going to be finite? Nothing.
Absolutely, yes, right. I mean, the fact that you can get from somewhere to somewhere in a finite length path is not obvious, right? It's not. That's the question. Is it in fact, is the spectrum of path lengths to get from somewhere to somewhere mostly finite paths, right? Is the spectrum of paths that see it could be the case that. See, this is the part that's not obvious to me. I mean, I suspect that it's a slightly different dynamic. I suspect that what's going on is that it requires some more information. It requires basically the analog, as we talked about before, the analog of, these extensionality axioms or some such other thing, which is essentially some kind of coarse graining axiom, that it requires that to get to the point where you are not continually being confronted, where the things that you are looking at, because you have already done a bunch of modding out, the things which you then see are ones that don't tend to have these undecidable pieces to them, but that it requires that type of logic. It is not merely a matter of the structure of the pure metamathematical space. I doubt we'll have this feature. Just like I don't think that absent, our coarse graining of the physical world, that, the things we're confronted with will have reducibility. I'm just pointing out, I don't think, to me, it doesn't seem right that the logic is that that these are facts about arbitrary, multi-way systems, effectively. But maybe you think they are. I don't know.
Well, this is why I objected to thinking about it as a combinatorial statement, because they're not that. They're facts about multi-way systems and the way in which they are being explored, which is a dynamical principle that does not exist purely in the multi-way system.
But okay, so what does that have to do with? So your argument about time-like curves, space-like curves, etc., did not make reference to, any kind of coarse graining or anything.
But it made repeated reference to the fact that mathematicians follow this geodesic equation.
Yes, but that's a different statement. Well, whatever, I don't understand. I mean, I just don't think that, whatever, maybe you figured it out, but I don't think the logic is right here. I think it's look, I think there's a pretty clean story. Maybe you figured it out. If you have, I haven't. I mean, I thought I had understood a fairly clean logical flow, although I don't see how to get, it just seems, whatever. All right, well, I think I will try and read your bulletin again. Do you think that should explain what you think, or?
Well, I mean, that and the paper that Xyz and I are trying to write at the moment, which will actually explain it in some detail.
Okay.
But
well, maybe I should stop working on this until you have all of that. I think it's
I don't know. I mean, it's possible that I have fundamentally misunderstood everything, but
I don't think you fundamentally misunderstood everything. Here's what I think. I think there is a, I think it is possible to get a cleaner. I mean, and maybe you have this. It's one of these cases where it's very hard for me to tell because you have a way of thinking about these things which isn't, different people will have different ways of thinking about things and different ways of understanding things. And until the whole thing is completely clean, it's very hard for one person to explain to another person how it works. But, I think that I just think there's a logic to how this works that I think is a bit tangled.
Mm-hmm.
I think that, I think there's a, I think in the end, it's going to be something very clean. And I think, there's a bunch of things that, we've talked about at least 5 times. But, and I don't know whether it's making use of mathematics that I don't know, or whether it's just, I have a certain intuition about what kind of argument, what kind of logical structure this thing should have. And I don't think it's quite right yet. I mean, I think it's a question of what, plus the statement about, certain inevitabilities in mathematics. I thought I understood this about 2 weeks ago. I thought I understood what the story was. And I thought I understood that the story was that basically there is a certain, by virtue of the way in which we choose to set up axiom systems, that we choose to have this way of thinking about mathematics where we effectively don't care about proofs, we only care about the endpoints of proofs. That
right, which is a homotopy story.
Right. That implied a way of exploring mathematical space, or a sort of that our picture of mathematical space would have these features like not seeing as much undecidability as we might have expected, okay?
Mm-hmm.
But as I have tried to tighten this up, I have failed, right? I don't quite get all the connections here. I don't quite get how this all fits together. And it should be possible to say it in a way that is very, very clean. It's going to be a, if it's as general a result as this, it is also a very clean result.
And you don't think saying, the interior of an event horizon is homeomorphic to a point is a clean way of saying it?
I think that requires going, that requires going many, many levels up. I think there's a way to say it that stays closer to the ground. Okay, that doesn't go all the way up into sort of ideas about general relativity and back down again. That's my point. I think there's a way to say it where you're just saying, look at this multi-way system, okay? And look at the properties it has. You don't even go into proof graphs and things. There's a way to say it that is just in terms of the very straightforward, essentially combinatorial properties of the multi-way system. And I don't even think it's very difficult. I think there's going to be a way to say this that is sort of, that as soon as you, and again, I was in the process of thinking about this. I figured that you've already figured out a bunch of it, but I'm just not understanding it. I mean, I'm not understanding how. Right. So, I mean, the point is, you would expect an argument along the lines of, if you make some assumption about the way in which we sample this multi-way graph, for example, we only care about the endpoints, we don't care about the proof, right? That as soon as you say that, and maybe you make another dynamical assumption, like that mathematics progresses by following shortest proofs, okay? That it may be that those things on their own, in a purely combinatorial way, effectively imply something about, well, I don't know exactly what kind of implication they would have, because,
Okay, so you want to prove a relativistic statement but without using relativity.
No, I'm not saying that. I'm saying I'm happy to use relativity. I just don't want to have to go to the level of I'm trying to keep it at the level of, you have this multi-way graph. It's an idealization of mathematics. You
Right.
go look at that.
It satisfies certain continuum equations that are generalizations of the Einstein equations, but you don't want to use those.
I'm not saying necessarily that I don't want to use those. I'm saying that if that's the case, then, okay. What are the parameters in those continuum equations? I mean, you're saying the continuum equation says, okay, well, okay, then, I mean, that is the intuition that we started from. But, in other words, you're taking the limit, the limit of the future of mathematics, so to speak, where you have essentially a continuum metamathematical space.
Yep.
Right?
But you don't want to actually use that space, or
I don't mind using that space. I don't mind using that space. So I just think that there's a more direct way to get there that does not require using that. I just think there are a bunch of things that are well, okay, but your argument,
is that the interior of an event horizon is homeomorphic to a point. So in particular, all of the time-like paths have finite length.
Yeah.
That's it. And so if mathematicians follow geodesic equations, they will tend to find themselves on the interior event horizons in which all propositions are decidable. Each, just like a Rulio black hole is a theory of physics in our original formulation, each, metamathematical black hole is a theory of mathematics. And so we will inevitably be drawn to the ones where there is decidability as a consequence of gravitation. I thought I had a fairly clean way of formulating that, but
well, okay. So your claim, which seems okay, that's a slightly different claim. That's a claim that mathematics is led to places where it gets stuck.
Well, as I've been saying from the beginning, it's a statement that mathematicians follow the geodesic equation and that the weak cosmic censorship conjecture is true.
I understand, but that has the implication that you're claiming that mathematicians generically get stuck.
Well, they get stuck in the sense they find themselves in regions where time-like paths are finite. They get stuck in the sense that the statements are decidable.
Okay. Okay, well, that's an interesting claim, but so you're then saying that, okay, so and
So that's just it's a simple dynamical principle that, as far as I can tell, explains why undecidability is so rare in practiced mathematics.
okay, so
I thought.
the claim there is that just like in our universe, we'll all end up inside black holes in the end, or at least that's one point of view. Although we wonder what Hawking radiation looks like in mathematics, but that's a separate problem. So okay, so this is the claim that basically mathematics, if you follow geodesics, so we should be able to see that in a computer experiment, that if we follow geodesics in a multi-way graph, that we will wind up in a terminating piece.
Well, no, we'll wind up in an event horizon. I mean, eventually you'll end up in a terminating piece, but it might take an arbitrarily long time. Yes, okay, and so yeah, I mean, it's exactly the same computer experiment that we did for the black hole stuff.
But those are two different statements. The statement that we wind up in an event horizon, the statement that we wind up at a terminating with a terminating rewrite system. Those are different statements. Which statement are you making?
The first. I never made the second statement.
But then why does that have to do with decidability? The fact that it ends up
because the interior of an event horizon is homeomorphic to a point, so all of your time-like paths are finite.
But that means they terminate. That means eventually it's a terminating rewrite system.
Well, eventually you hit the singularity, but it can take an arbitrarily large amount of time before that happens.
Okay,
so it's weakly normalizing, but not strongly normalizing. Well, okay, eventually
it will eventually
might be strongly normalizing.
Right, but I mean, your point is, okay, so you say that most of the time, you're making the claim that most of the time you can't get out of this event horizon. In other words, that there is no future, you can't get to, there's no infinite future. There's only a finite future. Is that right?
Yeah. Yeah, I mean, of course, in any field of mathematics, eventually you will exhaust all of the decidable propositions. But this is an explanation of why those decidable fields tend to prevail over the undecidable ones.
Okay, so let's just understand this. I mean, I think that's a.
Maybe I'm wrong. Whatever.
No, I'm not sure you're wrong. I'm not sure you're wrong. But I think I think there are multiple pieces to this, and I think that's a clean claim. Okay.
I thought so, but you've got me doubting. Yeah.
I know. Look, this is the nature of these things. I'm telling you that I'd like to be able to claim that if you convince me, it'll definitively be true. I don't know if that's correct, but I think I'm sort of stupid enough about these things that eventually, I'm not going to understand it unless the argument is fairly short in the end. So, but I mean, okay. The claim here would be that for reasons like the singularity theorems, that shortest paths okay, first question is, you're saying shortest paths tend to get I mean, one clear thing I don't know. I mean, look, but by the way, I'm going to make a meta comment, okay?
Uh-huh.
At least in my case, okay? I would say that, and I think I maybe have achieved meta to the fourth or fifth on this by now. I have noticed that the pricklier I get, the less likely that I completely know what I'm talking about.
Yes, right.
So, therefore, even at a triple meta level, I'm slightly suspicious about this. But at a, and what I think also, what's frustrating about this, I'm pretty sure there's something really, really good here, but it isn't quite there yet. And I think that again, look, can we just walking through this one more time, because I really think we're quite close. Okay, you're.
By the way, I mean, I should say, of course, I completely agree that there's obviously more to figure out, and that's why I'm trying to do it. But
Yes, and yeah, go ahead.
The reason I'm getting frustrated, I think, is just that this. I thought we'd been through this several times, and I just don't.
I know. This is my planned stupidity approach. Okay, I don't think it's quite right yet. That's why I'm not agreeing. Right? That's why we keep on going through it.
No, fine. I mean, I'm okay with that. You not agreeing.
Yeah, right.
I want to know which part is wrong.
Okay, look, I don't know yet. Okay, I think there is just a very direct way to go. Again, let's walk through it again. We've got this multi-way system. It is an attempt to idealize mathematics. We think we understand roughly how the multi-way system idealizes mathematics. Let's walk through that for a second. We've got either propositions, laws of inference, whatever, but fundamentally, we've got something where mathematics progresses by by finding these theorems, which are essentially finding paths that go from one place to another. They can find a path that goes from true to some proposition, or they can find a path that goes from, one expression to another expression, right? So mathematics, the achievements of mathematics, the museum that mathematics generates, the book in the Erdos sense, is a collection of these connections in this multi-way graph for a given axiom system. Do we agree so far?
Yep.
Okay. So now the question is, as we take the continuum limit, as we ask ourselves there are a couple of points. First of all, one feature of mathematics is that we are used to getting these kind of jump aheads in mathematics. We're used to saying something a little different from what we do in physics, which is we're used to collecting these sort of, once we have a path, we put it in our bag and we use it again.
I don't see why that's different to what we do in physics.
Explain.
Well, that was the whole point I've been making about generational multi-way states and measurements, right? Those, each time you obtain a generational state in the multi-way system, that corresponds to a new measurement that you're able to perform.
Okay, fine. At that level, okay, so let's walk through that for 1 second, okay? So you're saying that every time we do something which is, a classicality, so to speak, we got a definite result, that corresponds to essentially a theorem that we are then going to reuse. So you're saying this is a definite fact about the world that we established. Go ahead. What do you say?
Yeah. So then, if you assemble a particular generational, you assemble a particular classical state, that classical state can then be used in future measurement, as a way of performing more complicated measurements in the future.
Well, okay, that's an interesting connection. I agree. This is the claim that generational states are like kind of, theorems in the bag. Okay, I more or less understand that. I think there's an analogy there. I don't fully nail down understand that. But let's take that. Okay. But in any case, so one feature of mathematics is it uses this kind of jump ahead idea, right? And it's collecting those. Now, I don't completely get, although I'm sure it exists, I was going to try and do some experiments to understand this, the relationship between these kind of, these transitive closure jump aheads and causal edges. Okay, I don't fully understand that. I mean, these things are, do you understand that? I mean, I think it's a well, okay, all right. So look, there's that part. Okay, then there's the question of, okay, if we've got this system, including this jump ahead mechanism, and we take the continuum limit. See, I think for me, there's about 10 concepts here, and they're all related somehow, but I don't get the string of relations between them.
Mm-hmm.
I mean, in this picture where you've got multi-way systems and you've got these jumping ahead theorems and things, where, and again, how do the causal edges show up in this? How do causal edges relate to this jump ahead business?
Well, so each application of the jump ahead will have a causal edge associated with the event that spawned the final state in that jump ahead.
Sure. In other words, the jump ahead arrow is an event.
Yeah, and you're saying that anything that makes use of that jump event couldn't have been performed unless you previously derived that jump event.
Sure.
Which is a causal edge.
But that jump event, it's a little different from our normal causal edges, right? Because that event goes between two distant states, each of which had an event, each of which had events.
Mm-hmm. But the second event couldn't have been applied unless the first event had been applied. So it's the same as an ordinary causal edge. It just happens to be that the events changed the structure of the rules, which doesn't happen in a normal multi-way system.
So your point is that every one of those events that was, let's say there were 3 events that came down to one event in the jump event, right, in the jump rule, that all 3 of those events have a causal edge going to the event that is the summary event, so to speak, right?
In effect, yeah. Obviously in the proof graph, they are compressed to a single causal edge. But yeah.
Okay.
I mean,
yes.
That's the key difference. I mean, sorry, that's an obvious point, right? That's the key difference between multi-way systems and proof objects is that in the proof object, the events act both on states and rules.
Right. That's what I was confused by before, right? So I mean, in a jump ahead event is causally connected to all its component events, right? Though in the proof graph, only one causal edge is shown here.
Right. Because it's transitive reduction.
Okay, all right. Because the proof graph is a transitive reduction. Is that right? It's a yes, that's right. Is essentially, it's not quite a transitive reduction of this thing with jump ahead events.
Mm-hmm.
Okay, so we've got these. We've got causal edges associated with the jump ahead events, and we've got ordinary causal edges. How many? Okay, we could generate a huge number of jump ahead events, right? The whole transitive reduction would be a whole transitive closure, rather, is full of jump ahead events, right?
Mm-hmm.
Are we imagining that we're filling in all jump ahead events?
No, we're only filling in the ones that have the subsequent events have causal dependence upon.
But in the exploration of mathematics, which ones are we picking? What are we doing? I mean, isn't the exploration
the ones that future events have causal dependence on? You don't prove all possible lemmas. You only prove the lemmas you need in order to prove the theorem you care about.
Okay, fine. Okay, but so then there exist, jump ahead events that are really worthwhile, that are really worth having, right?
Yep, the load-bearing lemmas.
Yes, but yes. So I was going to do some experiments and find out which jump ahead events are worth having, if you understand what I'm saying. Is that obvious to you from something that you know about proof graphs? Because it's not obvious to me.
You mean other than the load-bearing lemma calculation of just determine which, what the vertex out degrees are?
Well, I mean, I did that for the, I've done that multiple times for the actual proof graphs that come out, back from the, and I found nothing very interesting there.
Oh, really? Okay, I found a bunch of cool stuff.
About what?
About Spinoza, amongst other things.
Well, I mean, I'll show you what I found in
Mm-hmm. I remember.
Right. So this was the stuff you made these pictures that, so these are some what you're calling load-bearing lemmas now, right?
Yep.
But what do you take as the significance of this?
Well, I mean, those are just useful things to have proven.
I know, but what is the bigger picture of this? That these are, but I mean, are these what you think will be the lemmas which will end up being, I don't even know how to characterize what lemmas will be useful for the full future of mathematics, right? I mean, there clearly will be an answer. Which lemmas are the freeways that are worth building?
Mm-hmm.
See what I'm saying? But I don't know. Do you think you have a characterization of that? Because I don't know. I was going to do some experiments on it. I don't have a characterization of that right now. Right, but you seem to be saying that you do have a characterization of that. I mean, what is the significance, do you think, in the relativistic interpretation? What do you think the significance of these lemmas that seem to have many, that seem to have, higher in degree, more occurrences? What do you think their significance is?
Higher in degree. Well, for those are with the if for higher in degree they are the the ones for which there exist large numbers of redundant proofs.
What were you saying? You were saying the out degree,
right?
Oh, actually, this is some kind of other thing. This is some kind of page rank thing, isn't it? That we did here. I can't remember. Something like that.
Yeah, this may have just been looking at degree.
I don't think so. I think this was looking at something else. This was looking at some centrality measure or something. I've forgotten. Let's take a look.
I thought proof graph weighted just looked at degrees, but maybe I'm wrong. Oh no, yeah, it is centrality. You are correct.
Okay, but in any case, okay, but so we go forward, certain lemmas will be more useful than others because of the nature of the axiom system. For some reason, I don't know which lemmas they will be. Do you think you know which lemmas they will be, or what the significance of the fact that some lemmas are more useful than others is?
Well, from the systematic investigation that I've done, they tend to be the ones that are most general and kind of pseudo-definitional.
What do you mean by most general? How do you tell what's most general?
As in that they are close. Well, I mean, at some level, you could say that's a circular definition, that general lemmas are ones that get used in proofs of many further lemmas.
Well, for example, are they short?
They're short relative to the. I mean, they're algorithmically short. They're short in an algorithmic complexity sense, in the sense that they're close to the axioms, at least in the cases I've found. So I'm looking at a bunch from ethics, right? So there's same object x comma x, which follows very straightforwardly from the initial axioms. Equivalent free of x not exists y limited y x. Again, quite close to the definition of the limited predicate.
Okay, so what I found, I mean, I did this in NKS, right? Because I did this when I was looking at the Boolean algebra stuff. And I was looking at, I looked at things like which, what were the most frequently used ones, and which ones had the most, I think I did look a little bit at which ones had the most oomph to them, so to speak. And this is the lengths of proofs for different. Okay, but. Okay, so we don't completely know what these sort of. I mean, these are lemmas which we expect will have many causal edges going from them, to the future, so to speak, right? These lemmas that are important will have many causal edges.
Mm-hmm.
Okay. Which is to say, those many causal edges will presumably lead to deflections of geodesics. That is, we will, by a deflection of a geodesic, we mean that lemma is going to stick its nose in because it will be commonly used. So the fact that there's a causal edge from it to the future is a reflection of the fact that it's sticking its nose into these various geodesics. That makes sense?
Mm-hmm.
So it's saying that, what does it mean if the geodesics are, okay, first of all, what does it mean for the geodesics to be, quotes, straight? What does it mean if a bundle of geodesics maintains, because I don't know, like the Branchial space for this, for the, what is the significance of the Branchial space for the multi-way system of mathematics?
Well, I mean, other than statements produced by redundant proofs.
Well, or in the interpretation, they're things which are equal, so to speak. They are,
In the equational case.
yes. This is where, again, it's kind of confusing because there are these two cases running around, and I'm not completely sure how to bring them together. But they're things which are equal.
Or just propositions obtained, by the course of by the course of redundant proofs.
Fine. But you see, I don't know. Okay. We should go out and do our separate things here. I think this is not, for some reason, this is just frustratingly difficult to communicate about. Now, having said that, different axiom systems for mathematics are like different alien intelligences exploring the universe, and this is we have a meta level of that. I mean, look, I don't know. I mean, I feel like anyway, all right, I should let you go. I'm sorry it's late, and I'm unfortunately I had hoped this would be clarifying for me. It is not. It is utterly confusing, and I'm more confused than I started with. I mean, I thought I was about to do a bunch of experiments which would be clarifying, but now I'm I mean, it doesn't help that I think there's a frustrating confusion between this equational stuff and the which I don't think is really a real issue. I think it's a
no. I agree. I agree because of the topos structure.
That's a giant bird swooping in from the ionosphere or something to save everything.
Right.
Well, that part I don't understand either. Anyway. All right. Well.
Although equivalently thinking about it in terms of the find equational proof converting predicate logic to equational logic thing is also valid.
Yeah, well, that's fairly easy to understand, I think.
I mean, yeah, so that's all that's going on, right? You're taking something that's unidirectional and you're converting it into an equivalent thing that's bidirectional.
Well, I mean, the predicate can be anything you want. Equality is just one of them. I mean, that. And then you've got to make sure that you can have rules that transform these things correctly. And that's the point of your, yeah.
Can I give an example? Maybe this doesn't work. I was trying to find a minimal example that demonstrated this. But it's oh yeah, okay, that's reasonable.
What? Are you signing something?
Yeah, so like here's a unidirectional thing, like the kind of thing you would prove in an ordinary multi-way system, but converted as something that can be proved via equational logic.
Okay, so this is multi-way to equational. you're saying. Okay, so now what should I look at here? Should I look at this thing as a proof data set, or what?
I don't know. What do you want to find out?
I want to see it in action. What the hell is this? So this is
unidirectional rules. A goes to B, B goes to C, proving that therefore A goes to C.
Okay, but what are these things here?
Those are the equationalized versions. So we're scolomizing and then setting them equal to a Boolean tautology.
But that's versions of these things, or these are generic? These are boilerplate.
So the first 5 there are just axioms of Boolean logic. 6 and 7 are conversions of axioms 1 and 2 to Boolean tautologies.
I see.
So actually, probably that's something I should implement in fine string proof, is a one-directional string prover.
Absolutely. That would be highly, highly useful. Is it obvious how to do that?
Yeah, I mean, it's changing it so that rather than setting things to be equals, it sets them to be implies. Just as you say, it's just changing the predicate. I didn't realize this would be such a point of confusion. But
is it going to look any different? Is it going to look any different in the final thing it sets up?
I mean, the proof graphs will be a lot more complicated, right? Because I mean, this is a super simple theorem, but the proof graph is quite complicated because, it's having to do.
But the proof graph, I see. So the proof graph,
it's like basically in the unidirectional case, the proof graphs and things are going to be basically impossible to analyze because you're proving a theorem that's in predicate logic, but your proof is in equational logic. There's very little correspondence between the proof and the actual logical steps.
Right. I mean, it's not the most direct way to think about it.
No, definitely not.
Look, it's still bugging me. I don't get this thing about, assume geodesics are the way that mathematicians explore metamathematical space. Great. They also collect more theorems along the way. And, what causes causal edges? What causes causal edges is that you are making use of a previous expression and also that you're making use of a previous theorem, so to speak. Mm-hmm. Right? Okay, so the claim is that in the continuum limit, if you had sort of a flat space, that was sort of in which nothing made use of any previous thing, that's what will give you a flat space, is that everything is new, you can use nothing from before. I claim.
That's not a flat space, that's a vacuum space.
Well, but the issue is what causes there to be geodesics that just go out you know, where the GD6 don't converge, et cetera, et cetera, et cetera. They just well, the question is, in this continuum limit, the claim is that the, you know, the deflection of GD6 is associated with this making use of previous stuff, right?
Yeah.
Right, that's what causes the deflection of GD6. So in meta-mathematics, what is the interpretation of a bundle of GD6 that just go on their merry way and don't diverge or converge?
Well, that's like the flat space pictures in my bulletin, right? The ones where you don't have non-trivial, you know, where all of your holonomies are trivial.
Yeah, I understand, but what is the significance of those for meta-mathematics?
Those are easy to, you know, those are proofs along which the algorithmic the computational complexity of proving things is as minimal, you know, is as small as possible.
As opposed to places where you are necessarily making use of previous facts, i.e. causal edges, at which the proof is no longer as direct. Is that the correct intuition?
Maybe, I don't know.
But do you see what I'm saying? I mean, that is, you're saying there is a deflection to this geodesic, which is the thing that is the exploration. There's a deflection to that is produced by the fact that it is that there are things from the past that are still affecting you.
Yeah, but that's the statement of the Einstein equations.
I know.
Yeah.
I'm just trying to state these things in terms that one can understand for meta-mathematics. That's saying that the statement is new things depend on old things. That's basically the claim, that these causal edges are affecting something in the future, right? And
well, their density is influencing the number of critical pair lemmas, and hence the density of non-trivial holonomies. Yes.
I think it's the same as what I'm saying, I think.
Well, it's the problem is in what you're saying, I don't understand what deflection means, you know, unless you have a notion of a holonomy.
Yes, it means you need a holonomy because you need multiple geodesics that are doing different things. Otherwise, you don't know what it means to go straight or not to go straight.
But multiple geodesics doing multiple things is what a critical pair lemma is.
I understand.
Right. So again, I think in the statement I made in the bulletin was Einstein field equations should hold in the space of all possible mathematical proofs. These will assert that the level of abstraction of the proof, i.e. our abstraction of the energy momentum tensor, should be directly related to the density of critical pair lemmas, i.e. our abstraction of the Ricci curvature, or correspondingly a proxy to the computational difficulty of generating the proof. We may think of the presence of causal edges as being an indication of the degree to which newly proved lemmas build upon previous results, which may in turn be interpreted as a crude interpretation of the degree of mathematical abstraction used within the proof.
Yeah, that I'm not totally, I mean, we talked about that before, but I'm not totally convinced about that.
Right.
But, okay, so from this, right, then this idea, well, whatever. This claim about singularities, it may be correct. Something like it may be correct. I don't completely get it. I mean, you're saying that as soon as you have this, there is an inevitability to the convergence of geodesics. As soon as you have something where the presence of past information causes these geodesics to converge. By the way, I don't understand why they necessarily have to converge rather than diverge. Is that obvious?
Yeah.
Why?
Well, because the more previous results you can build upon, the more different ways of proving the same expression there will in general be, because the more possible rewrites you can apply.
Okay, that's right. So it's all positive mass.
Right.
There's no negative mass. Okay, but then, so your claim is that there are inevitable singularity theorems that say that you must have convergence of geodesics, and so how would mathematics avoid this? How would mathematics avoid convergence of geodesics? Answer: by not building on previous results. The sort of virgin territory mathematics, which is kind of what happens in the NKS business.
Mm-hmm. Right. Well, I mean, this explains why undecidability is rampant in the computational universe, but not in practice mathematics.
So the claim is that as soon as you're using previous results, your proofs inevitably converge. That's the basic claim.
Right, and once there's a minimal amount of proof redundancy or proof convergence, then you have inevitable decidability.
Well, that it's inevitable that they converge, basically, that they end up. How does this relate? Okay, so I mean that's interesting, and that sounds about right. That as soon as you're building, as soon as you can make use of previous results, things snowball and it becomes decidable, basically, is what you're saying.
Yeah.
How does that make use of any of these extensionality axioms and so on? How does that make use of the fact that any concept about mathematicians? Well, I see. The key idea is that you can put a proof in the bag, so to speak. Right? If you couldn't do that, if you were always reproving, right, that would be a different story.
Yeah.
Right. So the key fact.
Univalence is the thing that allows you to convert between the path and the axiom that you subsequently use in the future proof.
Right, but so you know, the critical fact is you put the whole proof in the bag and use it, and use it as a one-step theorem, so to speak. Now,
which is univalence.
Explain that statement. Why is that not obvious? I mean, is that? I mean, why isn't that like just because of the structure of how you set things up? I mean, in other words, could you imagine?
It is. It's because of univalence is the structure of how you set things up.
I think I'm finally beginning to understand this. I think this is all finally making sense. So the key claim and then there's this whole set of things about model theory, right? And your whole set of ideas about, I mean, I was looking at, I mean, it turns out, I mean, I have these definite models based on operator, you know, these operator systems and things. I don't completely understand, you know, those operators will color, I mean, one of these multi-way graphs, basically. They will give you equivalences between expressions which otherwise wouldn't necessarily have equivalences.
Mm-hmm. Right. I.e. a reference frame.
Yeah, although they go and do it all the way down the system. I mean, they don't feel as space-like as a normal reference frame.
A reference frame isn't space-like.
Well, what I'm saying is,
a reference frame is extended in time.
Yeah, but it's in a series of slices. What I'm saying is that what this is going to do is it's going to say
only because we, you know, we format them in terms of, you know, level sets of a time function. The reference frame itself is just the time function.
Well, but look, what this operator thing is going to do is it's going to say this, you know, it's going to say a bunch of these strings are the same in terms of, you know, with this operator, a bunch of these strings are the same.
I know,
right?
It's defining an equivalence relation on states.
Indeed.
Yeah.
How do we use that equivalence relation? So, I mean, we can color this by these things are equivalent, right? We're going to have an additional set of connections here because of that. And I'm trying to understand, how does that relate to, I mean, in the relativistic case, what you know, it's going to say a bunch of things are equivalent here, right? How do I understand that in terms of foliations in the relativistic case? Did that make any sense? I mean, in the relativistic case,
yeah, of course it makes sense. I mean, it's just, I mean, but I don't know what answer you want me to give. It's just, you're defining an equivalence relation between elements that are potentially anti-chains, just like in relativity.
Okay, so hold on. So there are anti-chains which are right, but okay, but look, unlike in relativity, where what I'm doing is to say, if I'm not mistaken, I can say these things are simultaneous, right? That's an anti-chain, right? There's an anti-chain and certain things are simultaneous on that I'm going to identify this is the anti-chain I'm going to choose to identify. I'm going to choose to identify this sequence of anti-chains, right? When I interpret these in terms of operators and I say this one is a 2, this one's a 3, etc., 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 how do I relate that to a sequence of anti-chains?
Well, the choice of the model defines an equivalence relation that's just like the simultaneity equivalence relation of relativity.
Is it? The choice of the model, no. In this case, it's not right. It's not what it does. Because the choice of the model here, well, again, it's this stupid thing about single-way arrows and two-way arrows. You see what I'm saying? I mean, I don't understand this again. Because the operator business will take each of these and essentially give you a coordinate for each of these, right? That's what it means to interpret the concatenation as an operator with a definite multiplication table, right?
Yep.
It gives you a coordinate for each thing. It just, for each one of these, it's going to give me some definite number. Okay, this one might be a 7, that one might be a 7 up there.
Yeah, I understand. Yeah, please make whatever point you're trying to make.
I don't understand how that allows me to get... How does that allow me to make foliations, you know, anti-chain-like foliations? Is that obvious?
Well, yeah, again, it's the same as in the relativity case. It's the same as what we discussed the other day, and it's the same as what I described in quite a lot of detail in the bulletin. What is it that's not... Again, did I miss something?
I don't know. I'm just slow. Okay, whatever. I mean,
So like, you know, the example I gave in the bulletin is you have the pair of states AABB and ABBA, which are not syntactically provable because they form an antichain in the ordinary unfoliated multi-way system, but we can define a model in which that, you know, in which that implication is true, and that sets up a foliation. It sets up a global reference frame.
I understand that. I'm asking about the case where, yes, I get it. I'm asking
so
about
exactly the same is happening here. You're introducing new propositions that were not true in the original system, or were not.
It's just that there's an infinite collection of them. That's what's confusing. When you pick a particular operator, it produces an infinite collection of relations.
Sure.
That's what's sort of confusing to me.
Well, the foliation is global. That's okay.
Fine. I understand that. All right. That part I understand. All right. Well, look, I'm making progress in understanding this. I'll go read your bulletin again, or try to. I'm very bad at reading things, but I will try.
That's okay. I'm sorry. I'm sorry we didn't figure out more stuff.
Yeah, I mean, I'd like to be able to get, you know, for example, it would be really nice to be able to see in the Euclid case, for instance, can we see this in action? Can we see, you know, look, the fundamental point here, okay, the fundamental point is, you know, fields of mathematics that take on more and more previous facts wind up eventually being decidable.
Right. In the presence of sufficient abstraction, at least in the sense that I've defined it, black holes become inevitable.
No, but it's a different thing. It's almost like as you.
Why is it different?
Well, that's a more elaborate way of saying it. I'm saying something much simpler. I'm just saying, if you have an area where you just have more and more and more theorems that build on each other,
which is the abstraction density as I've defined it. Yeah.
I'm not sure that that is abstraction. I think it's something a little different.
No, I agree. You disagree with the. I understand you don't like the name, but that is abstraction density as I have defined it, right? As density of causal edges. So
yes.
Why is your claim different to mine? Is what I'm trying to ask.
I don't think it is. I'm not claiming that it is.
Okay.
I'm just saying that I'm just saying the only difference is that I think I understand it. That's not saying it's different. That as you build up more, but it is a level of statement that that makes sense to me. It doesn't, that as you put in more, as you accumulate more theorems.
But as theorems build on each other more, you get more redundant proofs. You get convergence of geodesics.
Yes.
The limit of that process is decidability.
Exactly.
And from a model theoretics perspective, non-constructivism. Because at the event horizon, all pairs of points are separated by light-like paths.
So the event horizon here is the edge of, is the border of this region of decidability.
Right. It's what separates this particular field of mathematics from others.
I mean, look, this has some significance. This picture is interesting, and it has the significance that what it implies is that fields of mathematics burn themselves out. Okay? That's a pretty interesting claim. Right? That in other words, what happens is, and it's not ahistorical. I mean, it's not.
There's a finite number of decidable propositions.
In the end, by the time you're accumulating a field, so to speak, but there are plenty of axiom systems. See, this is what's confusing. You just pick an axiom system, right? Then there may very well be undecidable, have lots of undecidability. But what this is saying is that that's what I don't understand. Okay, let me walk through this one more time. You have an axiom system. I pick it, right? My axiom system is Boolean algebra, right? It's going to be decidable. My axiom system is group theory. It's going to have a bunch of undecidability in it. Okay? Now I start doing my mathematics. I start exploring mathematical space. Okay? I make use of, I keep in my bag more and more theorems that I've discovered. Okay? And the claim is that there still are paths forever, presumably, that evade the singularity, but they become rarer and rarer. That has to be a claim. There has to be some claim like that, because the underlying axiom system is still not decidable. Nothing's going to make it decidable.
Right, but you're making one has to make the dynamic hypothesis that the mathematician is obeying a geodesic equation.
But is that enough? Is that enough to say, if you assume that the exploration is through geodesics?
Yeah. That's enough to guarantee that you will eventually terminate at the singularity, yeah.
Okay, so metamath is explored on geodesics. Okay, so the logic is metamathematics is explored on geodesics. Therefore, the claim is, therefore you don't get to see all the theorems, that will be the claim, of this axiom system. That would have to be the claim. That there are theorems. What's that?
The claim is that you're constrained to operate within the region of decidability.
Okay, the claim is if you follow geodesics, right? In other words, if you are a slave mathematician rather than a creative mathematician, jumping out and not following the shortest proof, right? So the claim would be, if you don't if you follow geodesics, then as you accumulate more theorems, your geodesics are pulled into a black hole and your area of mathematics becomes fully decidable. right? Even though the axiom system that you originally used. So your claim is that the reason this happens, if it happens, is because people are following Geodesics. That if you didn't follow Geodesics, you could escape. Is that your claim?
Yeah.
Now, does this fact depend on? I don't think this fact then depends on. But I don't understand, because there might be a proposition that can only be reached. I mean, does this fact depend on the fact that you're putting theorems in the bag, so to speak?
Yeah, it depends on the Einstein equations.
No. But does it depend on this jump ahead phenomenon?
Yes, it depends on the Einstein equations.
Why is that the Einstein equations?
The Einstein equations are the thing that tell you the relationship between abstraction, in my definition, which is the amount of previous results that you're able to build upon, and the density of critical pair lemmas. And it does depend on that.
But it depends on the fact that you are. Okay, so it's arguing that if mathematics progresses in this way, then it necessarily burns itself out and cannot even discover all the true facts of that given axiom system. Right? That's the claim being made here.
Mm-hmm. That
with this model for doing mathematics, that mathematics, I mean, which may be a correct model, but it's assuming, I mean, I think I finally understand, right? I think this logic works. This is explaining a thing that. So the long term, and then I suppose you can get to a higher level here, which is what you look at if you look at the space of all possible axiom systems. Do you get the same phenomenon there?
Yeah, I think so.
So in other words, in the Rulial multi-way system, if you were to explore there, you would find the same thing. I bet you would. Yes, I think you have to.
Because you have multiple singularities, each one of which has its own event horizon. If you're following a geodesic equation, you'll eventually end up in one of them.
So what does this mean for mathematics?
Like I've been saying, I think it explains why mathematics is decidable. Why so much stuff in mathematics is decidable.
I know, I understand that, but people won't like the fact that they're, ahead of them is a singularity, right? All the mathematicians are being drawn into this space-like singularity or something.
Yeah, but the set of decidable propositions is finite anyway. We know that in any finitely axiomatizable theory. So yeah, I mean, fields of mathematics have a finite shelf life. But yeah, that was going to be true anyway.
Well, it isn't. Look, wait a minute. There's an infinite collection of true theorems, even in a general theory which has undecidability, of which piano arithmetic is an example. Number theory doesn't stop. There's an infinite frontier for number theory.
That's what I'm saying.
What's that?
Yeah, sorry, go on.
But what you're claiming is that with a particular approach to doing mathematics, you cannot reach that infinite frontier.
There's only an infinite frontier if things are not cumulative. Right.
And this geodesic assumption.
Right.
Which is a little bit weird. I mean, if you say, I'm going to explore mathematics without looking for shortest proofs, what is that intuitively? What's going on there? You're wandering. You're wandering off the path. You're not, this is the anti-Erdos, right? So he had this idea of proofs from the book, right? This is saying if you follow proofs from the book, you're toast. You're going to wind up inside a black hole.
The geodesic equation thing I don't think is weird, right? It's just saying that we tend to make conjectures that are not particularly far from what is currently known. So you're piecewise constructing an approximation to a geodesic.
Yeah, fine. I understand that. I understand that statement, right? And which is different, by the way, from computer experiments, which don't do that.
Hence why undecidability is so rampant in the computational universe.
Well, okay. This is very cool. Okay. I mean, this agrees, the claim that I've made historically about why mathematics, okay, so it's close to, but not quite the same as the claim that I've long made about this, right? The claim that I've made is precisely this claim that it doesn't go far away from, that it doesn't do things which are going to go, that it keeps on this path and doesn't go off into undecidability. And the claim that I've made,
principle that explains why.
Right, but then, so the additional thing that I've claimed that may or may not have a useful mapping is that mathematics tends to generalize by asking that theorems remain true. Is that related to this? I think that is related to this. I think that's the statement that you're going to reuse the theorem.
Yeah, that's univalence. Yeah. You keep exploring new paths, but you retain knowledge of the paths that already existed.
Right, exactly. But the claim that I made, my attempt to explain the phenomenon previously, right? My historical attempt to explain the phenomenon was that the method of generalization in mathematics tends to stay.
Yeah, tends to preserve truth. You didn't,
Okay, now I get it. I'm very slow. Sorry. Yeah, okay. That's cool. It's a proof. I mean, it's a, see, but more interestingly, it's a theory. It's something which has really never existed before. It's essentially a dynamical theory of epistemology.
Right.
Well, very impressive. Okay. I mean, okay. All right. That is. There's some experiments to do here. But what's that?
Yeah, no, I agree. It'd be interesting to see them.
All right. Well, that did make progress finally at the 11th hour. I mean, no, this is very good. This works. This all fits together. I mean, again, this is what's been driving me frigging crazy. Because this type of argument, right, is, yeah, I mean, yeah, I like it. I mean, this is the proof of why studying the computational universe is doing more than mathematics.
Right. It's not following the same dynamical principle.
Well, it also is okay. It's very interesting. I mean, I'm sorry, just from the point of view of sort of, I mean, this intuition and these historical claims, right, I've obviously had for a long time. But this way of understanding them structurally and mathematically is just really fascinating. I mean, that's really interesting. I mean, I think, I mean, this non-constructiveness thing, I mean, I don't know what the general view of what a model is. Do you think you know what the general view of what a model is?
You see, you don't think it's a reference frame?
I think it is a reference frame, but I think that there has to be a way of explaining that. You know, it's a way of, okay, look, in the NKS book, the way I describe models is mostly in terms of these multiplication tables. Right? But to me, and you know, what I made the claim is that's the definition of when something is about something, is when it has a particular multiplication table. But I feel like a model being about something, that isn't, I don't find that very satisfactory as a description of what it means to be about something.
Mm-hmm.
If you see what I'm saying.
Right.
Right. So what does it mean? How do you say, when you say something, you know, some axiom system is about something, you know, I was trying to, it's like to be about something is to be, yeah, really what it is. Yes. Here's the way of thinking about it, I think.
It's a total order. Or close to one.
That's one way to think about it. But the thing I was going to say is something, yes, a total order, it is making deterministic. That's what it really is, you know, to be about something which is the same as to say it's a total order.
Right. Right.
To be about something is to make everything deterministic, i.e. a total order.
Right.
And so your claim about non-constructivism, your statement is you can't make a total order if you are going at the speed of proof, so to speak.
Mm-hmm. Right. A total order exists, but it's non-constructible.
What do you mean it's non-constructible?
As in, with any, you know, with finite computational resources, you cannot witness it.
Right. The total order is so much of it's so squiggly. You can't pre-compute the total order.
Right.
Well done. All right.
Have we resurrected your metamathematics post?
Maybe. I'm getting that. No, this is great. I mean, there's a ton of stuff I don't have to talk about because I don't think it's relevant. I mean, I think it's I mean, I think the other question is, you know, the role of things like category theory as a transportability of structure in mathematics.
Uh-huh.
I mean, that's a different issue, which is the statement that mathematics has repeated patterns.
Right.
As reflected by category theory. I don't know whether that's a part of the story. I think it is a part of the story because I think that is showing through the meta-mathematical character of mathematics.
Mm-hmm.
Right. That's why it's you know the transportability of category theory.
I mean, yeah, you could probably make some very precise correspondence that category theory is effectively parallel transport between bundles of geodesics.
Yeah, right. But that's because there's a uniformity of meta-mathematical space.
Mm-hmm.
That in the continuum limit, meta-mathematical space all looks the same.
Right.
What's the dimension of meta-mathematical space?
You mean what's its significance? What is its numerical value?
Yeah,
Well, it's infinite.
7.4. It's exponential, right? But I mean, mathematical space is exponential. But what's the exponent, and is that significant? It's probably not definable. That depends on representation.
Yeah, I was going to say it's a Chaitin's constant kind of thing.
But and what's the expansion of the mathematical universe? What is that? What is the significance of that? I think that's all of the computer experiments you could do.
Essentially, yeah. I mean, well, I mean, the way I was going to say it is, branchial space parameterizes the degree of speed up of quantum computers over classical ones, then expansion of Rullial space sort of quantifies the degree of speed up of doing computer experiments versus doing mathematical proofs.
You're saying the expansion of the extra size of Rullial space.
The expansion rate, right?
Maybe.
It's only advantageous to do, the big question is why do NKS if you could just do mathematics?
Right.
And so it's only useful to be able to, if Rullial space were not expanding, then there'd be no difference.
Right. Expansion of Rullial space means NKS is necessary. Math will never reach, math can't go fast enough.
Right. Yeah. So NKS is the quantum computer, math is the classical one.
Yeah. And now it's time for my dinner, and I'm sorry to have kept you up. So
No, it's okay.
This is good progress. I appreciate it. I mean, I am but the tortoise.
No, it's good to sanity check these things, right? I mean,
yeah, no, but the thing is, look, there are these mathematical proof methods which you use, which I'm not so into. I just mostly do experiments, but look, I think I get this. I think this all makes sense. This fits together. This is good.
And okay. Well, if we can translate what I've done into something more concrete, then that would be helpful.
Yes. Yeah, and I should reread, now that I think I understand it, I should reread your bulletin. No, I mean, it's look, it also doesn't hurt, okay, I need to go and have my dinner, but I mean, one of my principles about this thing, okay, which is a difficult principle, is just because I believe things based on various intuition that I've had in the past doesn't mean that, in other words, I make an active effort to not prejudice the outcome with things that I believe to be the case in the past.
Right. That's a noble way to proceed.
Well, it's because a number of times in my life, major things I've discovered were a consequence of the fact that, that I was able to do that, even though I failed to do it at first. And, the fact that this beautifully dovetails with what with the sort of historical theory about how mathematics works is just absolutely terrific. I mean, it's really terrific. It's very cool. All right. Okay. See you later.
Great. Okay. Thanks.
Okay.
All right.
Okay. Bye.
Bye.